Okay, so we will get started with our first lecture for the week. I just realized 2 minutes ago that I've been introducing the lecturers and I'm the lecturer now. So I guess I will introduce myself. You've heard already enough number of times from me. My name is, you see it spelled here, contrary to popular belief. My name is said as Kishalay. For 5 years, I tried to convince my PhD advisor to say it right, and I couldn't, so I gave up. But Kishalay is the right pronunciation, at least the way I'm called back home. Right, I am an assistant professor at Columbia and jointly associate research scientist at CCA. I'm one of the co-organizers for the school, and a lot of what I'm going to talk about today is stuff that I think very passionately about. It's stuff that I learned when I was in grad school. I did my undergrad in the Institute of Science, and then I came to the US. I got my master's and PhD at Caltech. And the reason I'm mentioning this is because I happened to land at Caltech at a very interesting time. It was the last year of operations of the Palomar Transient factory. Anybody here of the Palomar Transient factory? Okay, good. Okay, so most of you have heard of PTF. So it was the last year of formal operations of PTF. And right after I arrived, maybe 6 months later, they took off the camera from the 48-inch telescope at Palomar. And then they put on what you know today as the Zwicky Transient facility, which is the exact same telescope, but just uses a much more advanced, bigger camera that's been running for, yes, now almost 8 years now. So the reason this is interesting is because when I started grad school, I got a very close-up view of how a survey runs and how do you build a survey from scratch, especially when ZTF was being commissioned. And so that was obviously, quite an enriching experience. And then I went on for the second half of my thesis. I went on to go and build my own survey. It's a survey called Gattini IR, which is a wide field infrared surveyor. How many of you have heard of Gattini IR? Okay, lesser, but okay, thank you. Okay, somebody's heard of my PhD thesis. Okay, good. Right, so what I'm going to talk about today is essentially how do you take a telescope? If I gave you a telescope today, how do you turn it into a survey? And how do you quantify how does this survey compare to other existing surveys out there? And it turns out there are interesting mathematical ways of quantifying that. And the entire reason I'm doing it is because these 2 weeks have all been about LSST, about the data revolution that LSST is going to bring and what that is going to do for survey science. So it's somewhat apt to think about why are we so excited about LSST in a mathematical sense? What is the big deal about LSST? So just to make sure that all of you are awake, I'm going to give you 5 minutes, find a friend next to you, and come up with some points about what makes LSST what it is. Like, why is LSST better than what has been done before? Start.
You're so much pressure.
Yeah. We didn't plan it.
Well, let's file it up.
So there's sort of
Yeah, you're better off the biggest camera ever. Yeah,
yeah, we have the
Yeah, I guess more
like 2 weeks. They're repeating areas because of area. So it's not better than which is why to that that must be a factor.
like, but I think you don't even but they have, I guess, the idea that it's so unique about like imaging biology and like technology. But I've heard that
All right. Okay. So we're at 5 minutes or 4.5 minutes. So we can start wrapping up and collecting all the conclusions we found in 5 minutes. All right. I need volunteers. Someone tell me what is special about LSST. Yes. Go ahead.
Gallons of the universe per minute.
Sorry, what?
Gallons of the universe per minute.
Okay. So it's like how much volume of the universe you're probing per minute. Okay. Any other answers? Yes. Go ahead.
Well, I mean, like the magnitude limits.
Right. Yes. Magnitude limit, which is a very deep survey. Yes. Anything else? Yes.
you have more filter information like U-band, especially.
Right. Yes. Lots of colors, 6 filters for LSST. Yes. Good point. Anything else? Yes.
I learned from my seatmate that there's something special about the camera or the CCD, that the like information depth, so the
Yes.
detail that you get,
Yes.
you know, per little area
Yes.
is much more than perhaps like say ZTF or something.
Right. So put in other words, LSST does have lots of pixels, which means you get higher spatial resolution per pixel compared to other surveys that have been operating in the last few years. Any other? Yes.
It's supposed to have really good photometric and astrometric precision.
Right. Excellent. Yes. So it's going to be a super precise measurement machine. So if you can if your application requires high precision measurements, that's great. Anything else? Okay, I think that more or less summarizes sort of the main points of LSST. So what we'll try to do in this talk is formal. Yes, sorry. Yes.
A question about the photometric measurements.
Yes.
Like how does it compare with like Gaia or like all of like this emissions?
Right. So Gaia is very precise, but it's usually for fairly bright sources. So things that are maybe 16th, 17th magnitude or brighter. LSST goes down to, at least I think the claims for the precision are down to about 21st magnitude. In principle, you can see fainter sources out down to 24th magnitude, but the precision has been promised to about 21st magnitude level. So it's about a factor of 100 deeper than, if you talk of the same precision threshold, then LSST can be about a factor of 100 deeper. Of course, LSST as a ground-based survey does not get the parallax measurements that Gaia is great at because it's in space and you can do very high spatial resolution photometry. Right. So what we're going to try to do for this talk is formalize some of this in a mathematical sense, as in what if somebody asks you how does LSST compare to its predecessors, can I give at least one number that compares LSST to what exists today? And how did that come about? And how does that influence some of the design choices that you'll hear about from Igor later in the afternoon. So if you just go back to that. So what I did was I took this table from one of Eric Bell's paper from a few years ago, which shows a number of parameters of interest for different surveys that have existed in the past or are coming up. You see there are, what it shows is the first column is the survey name. The second column is the diameter of the telescope that's running it. And the third column is the field of view that it gets in square degrees. So it really spans a very wide variety of numbers. As you can see from the top, you have every scope, we have every scope representation in this room, which is great. It has this crazy wide field of view of whatever, 9,000 square degrees, all the way down to smaller instruments that have of the order of a few square degrees. So one of the things that we heard just now is this idea of LSST is going to be super deep, which partly comes from the fact that it's a big telescope. LSST, as you can see, is a 6.5 meter telescope. And when you have a larger collecting bucket, you get very deep photometry. And combined with that, what you get is a large field of view, which is about 10 square degrees for LSST. So what I want to sort of seed in your brain right now is this question of, let's say we have a number of big telescopes on there. You see HSC. HSC is the Hyper Supreme Cam, which is a 8-meter telescope on Mauna Kea. On paper, Subaru is a bigger telescope than LSST. It's 8.2 meters compared to the 6.5 meters that LSST is. And the field of view is obviously smaller, but you might ask that why hasn't Hyper Supreme Cam already done half of what LSST can do? Simply because the numbers are fairly close enough, maybe a factor of few off in field of view. And Subaru is a bigger telescope, so it can see much further away. So the question you can naturally ask is, why is LSST special compared to Subaru? Why are we thinking of LSST as a survey machine, whereas its predecessors like Subaru or a DE Cam, which have similar numbers, why are those not as commonly talked about? All right. So to begin with, what we need to start understanding is that actually, okay, so I want to ask this question because I've been surprised often. How many of us have been to a real telescope? Good, most of us. Okay. If you haven't, please, I recommend you, please go to and see what a telescope looks like. It's an extremely enriching experience. You finally get to see how much work it takes to actually make an observatory happen. Today, we have the luxury of sort of sitting on our computers and using data that's downloadable from the internet, but there's a lot of work that goes into these things. So I highly recommend you go and see some telescope and sort of get a sense of how big the scale of operations is for any, all the way from small to big observatories. So to begin with our discussion, what I wanted to start with is this basic idea of, let's say I give you a telescope. Can I start quantifying how faint sources can it see? So the way we do it normally is this idea of quantifying what a signal to noise ratio is. Everybody familiar with signal to noise ratio? Okay, good. So let's say I have a star in the sky. Let's assume it's a point source, which is more or less most of the things we're interested in transient astronomy. If I asked, how can I quantify what is the signal to noise ratio of a measurement? And how does that depend on the properties of the site, properties of the detector? This is something that we want to start formalizing. So if I write the signal to noise ratio as something like this, the noise in these detectors can be assumed to be a Poisson noise source, which means that if you want to quantify what the signal to noise is, you just signal and divided by noise. And this is the number of, let's say, electrons that from the source that I'm interested in, divided by all the noise terms. So imagine I have a detector that has captured an image of a part of the sky. There are a bunch of stars in it, like that. So what I can do is, let's say I'm interested in measuring the signal to noise of this source over here. What I can ask is I can put digitally an aperture on this source and ask how many electrons am I recording from this source. So let's call that, if I take this equation again, let's call that n star. which is the number of electrons I'm recording from this star on the digitally recorded image. And because this is Poisson statistics, what you get is that if there was no other noise source in the detector, we would get at least one noise source. What is that? Yes, the square, yes. So the minimum noise you will get from a Poisson process is the noise from the source itself, with that saying that if you're recording n electrons from a star, the minimum noise you will get is always the noise from the star itself, which is square root of n star. Okay. So, but there are some additional terms in there which makes all this survey science more fun. Can we start naming some of those? There are some additional terms that add to the noise that comes in the measurement. What other noise terms are there in this equation? Yes.
Sky background?
Yes, good point. Yes. So let's say the footprint of the star on the detector is some n number of pixels, then I can call this as number of pixels times, let's call it n sky, which is the sky background per pixel. Anything else? Yes.
Read noise?
Yes, good point. So let's say that again, n pixels is the footprint of your star on the detector. I can call it n pix times. Usually this is quantified as a square, as a variance of the read noise that you get from the detector. Any other terms in this? Yes.
Dark current?
Yes, dark current is usually, thankfully, not as problematic for optical detectors because these are cool detectors. But yes, you can have an additional noise term that is essentially, so everybody familiar with dark current? Dark current is the signal that you get from the detector, even if there was no light falling on the detector. It's effectively a thermal current of electrons that occurs because there are, it's a non-zero, the detector is at a non-zero temperature and it's constantly producing electrons because of thermal noise. And that scales with the temperature of the detector. So let's call it N dark. Okay. Now, so this is what defines, let's say I took my telescope and stared at the sky for some amount of time, then I can quantify what the signal to noise of any particular detection is. Okay. So we will ignore some terms over here, and I'll come very soon tell you why, which is one of the things is that dark current is usually fairly small for optical detectors when they're cooled. So we will set this to 0. Read noise can be important, but as we'll talk about in a bit, it turns out that this does not, well, surveys are designed such that this is not the dominant term. So we will ignore this for now. But what this ends up being is that the signal to noise is n star divided by the dominant terms end up being n star plus the number of pixels that the star occupies on the detector times n sky, which is the sky background. And the sky background is important, especially for ground-based observations, because we're looking at the star through an atmosphere, and the atmosphere is always in front of the star. So now, all of these terms have some dependence on the exposure time that we get that we use for this experiment. How does the number of electrons we are recording from the star depend on exposure time? What is the power law? If I crank up the exposure time by a factor of 2, how many more electrons would I record from the star? Yes, it's linear. Yes, so this is a term that scales with the exposure time. What?
You hope it's linear.
Well, yes, for optical detectors we will assume it's linear. Yes, so this term scales with t. How does this term scale? The number of sky photons that you're recording? Yes, it's also linear. Yes. So what you end up getting is that this fairly simple relation that it doesn't really matter what the brightness of the star is or what the brightness of the sky is. The signal to noise that you get from this just scales as square root of t, because t square root cancels out. Okay, which means that if I expose for, let's say, 25 times longer on the sky, my signal to noise improves by a factor of 5. Yes, thank you. Yes. So the signal to noise scales as the square root of the time that we expose for on the sky. And this is going to be important for the discussion that we are going to get into. All right. So everybody here of the Hubble Space Telescope, hopefully. Hubble Space Telescope, it's a, one of the premier observatories of NASA that's been running for almost 30 years now. Hubble really benefits from the fact that it's in space, which means that this term is effectively zero, well, or very, very, very small. The reason I'm saying this is that if you think of the limit where we are looking at very, very faint objects, which means that n star is much, much smaller than n sky, what you end up getting is that the signal to noise becomes n star divided by square root of n pix n sky. Okay. And this is again scale says square root of t. Is that obvious? Which is that if the brightness of the star is if it's a very, very faint source, then your noise term is dominated by the sky background, the sky foreground rather. And what decides the signal to noise ratio is really the ratio of the brightness of the star to the brightness of the sky. And this is why space observatories work really well, which is that if you think of things like Hubble Space Telescope and JWST, this term is very, very small because it doesn't have to look through the atmosphere. And outside the Earth's atmosphere, the sky is very dark. So you can go much, much deeper for a given exposure time. Okay. Right. Any questions so far? Okay. So here is a thought experiment I want you to think of, which is that what you're seeing here is that if I expose for longer, then my signal to noise for a given brightness of the star keeps increasing with time. Conversely, what that means is that the flux of a star that I can detect for a fixed signal to noise ratio scales as 1 over square root of t, right? If I fix the signal to noise ratio, you can fix it to whatever your favorite number is, 3, 5, 10. If you fix the signal to noise ratio, then n star, which depends on the flux of the star, the faintest sources that you can see depends inversely on the square root of time, which means that the longer I expose, the fainter sources I'm seeing. Okay, that's sort of, I guess, common sense, but this sort of formalizes all of that. Okay. So let's say I gave you a lot of time on any big telescope, any telescope that you want in the world, and I gave you this choice of, I want to, we heard of this thing called number of gallons per minute, was it? It's a very interesting unit, gallons per minute, yes. Yes, so the number of gallons of the universe you can probe with a given exposure. Let's say if you want to quantify that, what this relationship tells you is that as you keep increasing the exposure time, you can see fainter and fainter sources, which means that you probe more gallons in the universe. And so if I give you the choice, which is, let's say that you could either point your telescope in a given direction for a super long exposure time, or you could take short exposure times and keep marching through the sky, look at different parts of the sky. Which one do you think would be more effective for increasing the yield of a survey? So, the example I'm thinking of is that, let's say you have 10,000 seconds of time to waste on a telescope. What I could do is I could take, let's say, 10 times 1,000-second exposures, right? So 10 number of exposures, 10 times 1,000, each exposure is 1,000 seconds each. Or you could take 100 of these 100-second exposures, right? So 100 seconds, 100 seconds, 100 seconds, 100 seconds, and you do 100 of them. Or you do 1,000 seconds, 1,000 seconds, 1,000 seconds, do 10 of them. Which one of these things do you think would end up probing more gallons in the universe over this fixed amount of time? Any guesses? Because these are some of the choices we have to make in real surveys. So what you'll hear from Igor later today is things like what the LSST exposure time is, right? And it's not, I think, obvious for a given telescope, what should be my exposure time? I could take my telescope and point it at one part of the sky for a super long exposure and do fewer exposures. This is probing a deeper, further away in the universe, but a smaller area on the sky, whereas this is doing, much closer objects, but over a bigger footprint of the sky. But which one of these probes a larger gallons in the universe? Yes.
I think the longer exposure,
Mhm.
because your flux limit is going to be square root of 10
Yes.
times greater, and the volume goes as the cube of the depth. So,
Right.
You get 10 times less area, but you get square root of 10 to the 3 times more volume.
Right. Yes. So these are exactly the kinds of computations which you can do. What we are saying is that because the flux limit scales as square root 1 over square root of t, this, for a Euclidean universe where flux goes as 1 over r squared, this automatically provides some relationship between the distance that you can see for a constant population of sources and the exposure time. And the distance quantifies how much volume you're seeing. Okay. So these are some of the things that we'll try to formalize right now. But yes, this is exactly in the right direction. All right. Any questions so far? Good. So right. So let's start doing some of the mathematics that decides what this looks like. So we'll start by, well, again, formalizing some of the basic parameters of a survey. The first thing we can talk about is the second number that you see over there, which is the field of view. So what do I mean by a field of view? For just to make sure everybody is on the same page. Field of view. So we will assume that our telescope, which is not always true and definitely not true in the case of LSST, we will assume that the portion of the sky that we can see with one given exposure is roughly a square, which it is not in the case of LSST, but let's assume it is. So, oops. So this is the sides are given by, let's say, A degrees by B degrees. Then the field of view is just the area of this footprint on the sky, which is A times B. For LSST, this number is, we see it on that table over there. It's about 9.6 square degrees on the sky. For ZTF, anybody know the number for ZTF? Yes, 40 is about 47 square degrees effective on the sky. Okay. And for Gattini IR, which I mentioned was this much smaller infrared surveyor that I was working with, so it has a similar footprint, which has 25 square degrees on the sky. Okay. So this is one parameter we are interested in. We start. Okay, everybody done with this? I can start removing some of this stuff. Right. Now, this is of course tells you what the full footprint of the survey is on, well, of one exposure of the survey is on the sky. The other parameter that is somewhat overlooked but is equally important is this idea of a pixel scale. So I assume most of you have heard of what a pixel scale is. A pixel scale is that if I take this detector and I divide it up into obviously digital rows and columns, then what is the individual footprint of one pixel on the sky? For LSST, this number is, what is the pixel scale of LSST? Can you remember? LSST pixel scale? Yes, 0.2 arc seconds per pixel. So this defines how big the footprint of each pixel is on the sky. What is it for ZTF? You know what the pixel scale of ZTF is? Not you. Yes.
I actually don't know.
Yeah.
It's really embarrassing.
Yes, 1 arc second per pixel. So, okay. Now, the reason this is important is that this actually tells you why you commonly hear this term, especially in the popular media, about LSST is the biggest survey that has ever been built. Okay. The reason it gets its name is because if you take this field of view, which is about 10 square degrees, and you divide it up into 0.2 arc second pixels, each, this entire footprint being sampled by 0.2 arc second pixels, you can just do a division, 10 square degrees divided by 0.2 arc seconds per pixel. What you'll get is that the number of pixels in the LSST camera, number of pixels for LSST is about 3.2 billion pixels. This is why it gets its name the biggest survey. This is the largest astronomical camera that has ever been built. Yes.
So
Yes.
I'm a theorist, so I
Yes.
apologize.
Yeah, I know it. Yes.
Yes. What's the point of having a pixel size that's smaller than the seeing?
So the question is, what is the seeing? So LSST is in Chile at Cerro Pachon, well, close to the site of Gemini. There, the typical seeing can be about 0.5 or 0.6 arc seconds. So we'll not get a chance to talk about this, but in signal theory, you can show that there is something called the Nyquist theorem, which tells you that if your highest spatial frequency that is allowed is 0.5 or 0.6 arc seconds, you want to make sure that at least 2 pixels cover that full width at half maximum of the seeing disk. So ZTF is in a much crappier site, the Palomar, where the seeing is typically 2 arc seconds, which is why it's 1 arc second per pixel. But you're absolutely right. This is kind of one of the fundamental decisions one has to make. Yes.
In addition to what you said,
Yes.
Rubin will also have an adaptive optics system.
Right. Yes.
So that allows you to beat the scene on top of being on a good site. So
Right.
the resolution is going to be excellent. Thanks to the pixel scale as well.
Yes. Yes.
Thank you.
How is your largest astronomical camera ever built? What's
Yes.
the largest actual camera ever built?
I think this is the largest actual camera ever
Okay.
built. Yes. Sorry, when I said astronomical camera, because astronomers are the people creating big cameras. I don't think, yes. So yes, so building the camera alone was a huge technological feat. That's what made LSST possible. Like, people at Stanford have spent years of their life designing this camera because it's not easy to create. Our phones have typically what, like 10, 20 million pixels. That's the typical size of cameras on our phone. These are all CMOS detectors. This thing is a factor of 100 times bigger than that. I think the LSST camera is about the size of a human being. So that's how big the camera is. Okay. Now you can do a simple comparison. Number of pixels in ZTF. Anybody know this number? What is the number of pixels in ZTF, the predecessor? It's about 0.66 billion or 660 million pixels. So it's not, it's not bad. It's just, but not as big as what LSST is. You can do a similar number, and again, I'm pushing it to the other side because I want you to see the differences, which is Gatini IR, which was the project I talked about, was on a shoestring budget. So, and also it was in the infrared, but detectors tend to be much more expensive. The number of pixels in Gatini IR is about 4 million. 4 million pixels. So it's tiny. So the Gatini IR camera is much, much smaller in terms of number of pixels, but it has nearly the same field of view, or half the field of view of ZTF. How does that work? How do you have a camera that's roughly the same footprint on the sky, but has a factor of whatever, 100 smaller number of pixels? Yes, so the footprint per pixel is very large. So this is for those of you who worked with Assassin. Anybody care to work with Assassin? Assassin and Gatini IR are in the opposite regime, where we don't care about spatial resolution at all. For Gatini IR, the pixel scale is about 8.3 arc seconds per pixel. So it means that here you're severely undersampling the seeing PSF, and that comes with its own range of challenges, which is kind of why I had to spend 4 years of my life figuring it out. But these are the two regimes. Where Assassin, which was you see over there on this plot, Assassin is a similar game where you have giant pixels that allow you to cover a much bigger field of view on the sky for with a small detector. And that that obviously comes because the telescope itself is designed that way. Okay. Any questions about this? Yes.
So with Catini, was
Yes.
this really a cost thing, or was it that you just needed to see if there was a transient because you had something else you could follow up with quickly?
So I think if we had the option, we would have gone for a bigger detector, but it's just that these infrared detectors are incredibly expensive. So even today, the technology doesn't exist to build a infrared ZTF. The cameras are too expensive. So it was, I think, ultimately a cost thing. Right. Okay. So what we're going to, all of this sets us up well for formalizing some of these things of how do we compute the amount of volume that my survey is probing per unit time. So let's see. So let's talk about, with this setup of this field of view, let's talk about how much volume am I probing per exposure for a given exposure time. Okay, so this is what you'll commonly hear in many papers as multiple. It's been called multiple things. Some people call it a grasp of a survey. You'll also hear the term volumetric survey speed, which is, I think, more intuitive for what this means. Volumetric survey speed. So what this tells you is that if I use, let's say, X seconds of my telescope time staring at one part of the sky with the field of view that I have, how much volume of the universe am I taking a snapshot of per unit time, given the amount of time that I spent on that field? Okay, that's basically what it is. And what we'll try to do is formalize some of this with this simple Poisson statistics regime that we started with. All right, so what we already established was that the flux of the faintest source that you can see scales as 1 over square root of t, which means that the longer I expose, I see fainter sources. Right, yes. And to ask how far in the universe can I see with this exposure time, we will assume that we're interested in the same population of sources that are uniformly distributed everywhere in the universe. The most common comparison people like to use is type 1a supernovae because they're everywhere. Type 1a supernovae, I think, regardless, you could be in a star-forming galaxy, or dead galaxy, you'll get type 1a supernovae everywhere. And they're very bright compared to other forms of supernovae, which is why it's a common comparison standard. So in order to compute, let's say, how much volume am I probing in the universe? A common comparison is how many type 1a supernovae could I detect in this exposure, given my field of view and given the exposure time that I'm doing. Okay, so to make sure that my type 1a supernova is detected in my exposure, what I need to make sure is that let's say we're just interested in the peak luminosity, peak flux of a type 1a supernova. So let's call it this way. So to detect SN1A, I want peak flux of the type 1a supernova to be greater than the sensitivity threshold of my exposure that I'm interested in. So we know how this changes as a function of distance in a perfectly spherical universe. This is L peak divided by 4 pi d squared, which is just, this has to be greater than f star. So what you can show is that the limiting volume, limiting distance out to which you can see a type 1a supernova, that's what we want to compute, which is how much volume in the universe can I detect a type 1a supernova in. So, right, so if you take this, the limiting volume is then, limiting distance is square root of L peak divided by 4 pi f star. we already established that f star scales as 1 over square root of t, which means that the limiting distance out to which you see things scales as t to the 1/4. Does that make sense so far? That you have a square root of t inside a square root, so you get that the distance out to which you see a type 1a supernova scales with the exposure time like this, t to the 1/4. Okay, so if you ask how much volume am I probing a type 1a supernova in, then the volume scales as d cube, which means this scales as t to the 3/4. So that is again a fairly straightforward relation. What that tells you is that as I keep increasing the exposure time of a survey, the amount of volume that I'm probing in the universe for any type of source scales as exposure time to the power 3/4. Yes.
Why does it scale as d to the cube? I'm just like picturing like the field of view times the depth, or like what?
Oh, sorry. So sorry. Yes. Well, there's a prefactor here. So what I'm saying is that let's say your field of view is fixed. Your field of view could be the whole sky. Then it's just 4π/3 d cube. If it's not the whole sky, then it's some smaller fraction of that. So let's say you had an ideal survey where you're looking at the whole sky at any given time. Then your volume is 4π/3 d lim cube, right? But let's say you are probing only this part of the sky, which is any realistic survey, then you multiply some delta omega over 4π, which just tells you the fraction of sky that you're seeing, but it doesn't change the time dependence. It's a constant multiplier to the volume that you're seeing. Okay. So that's a good point, which is if you do it more exactly, then the limiting volume that you see a type 1a supernova in is actually delta omega, which is, let's call it the solid angle over which your survey is seeing the sky, divided by 4π, which is the full sky, multiplied by 4π/3 d cube. Okay, this also has the same time dependence, which is it scales as t to the 3/4. Good. All right, we're getting there. We're almost there. We'll see why LSST has 15-second exposure times very soon. Any questions about this so far? All right. So we are getting there. What we said so far is that let's say if I expose on the sky for some exposure time, then this is the amount of volume that I'm probing. But not with any realistic telescope operation. Let's say you slew your telescope to this part of the sky, you take a somewhat longish exposure, and then you move to the next part of the sky. Okay. So this is the amount of volume I'm probing. This is the gallons we're interested in. How do we get the number of minutes that how many minutes is it actually taking us to cover this amount of volume in the universe? So there's obviously the exposure time, which is the minimum because I have to expose for this long to get my volume. What other things do we have to account for? Well, between two exposures, does the telescope instantaneously move to another field?
Yeah.
Yes, and
They overlap.
right. So it takes some amount of time for the telescope to, let's say, read out the detector, right? Any CCD has a finite readout time. It takes the telescope some time to slew across fields, right? And let's say if you're doing infrared observing, for example, you have to dither between exposures and all of that takes time. So in the end, what you end up doing is that, yes, you're probing this volume in this amount of exposure time, but on top of that, you have some overheads that we have to account for, okay? So what kind of overheads do I mean? So what we'll try to quantify is that how much time does it take me to actually see this amount of volume in the universe? And if I go to a particular pointing of the field, let's call that a visit, the amount of time it takes me to do that visit at minimum is the exposure time that I do, right? We can't get rid of the exposure time. This is what we need to be able to see that deep. In addition to that, we have things like, let's say, the readout time of the detector. We can have the time it takes to slew, and there can be other terms depending on the telescope, which will not go into super detail about. But essentially what I'm saying is that the total visit time is always at minimum the exposure time that I need to gather all the photons that I need, plus an overhead time that I'm interested in. So the overhead can have many things in it, and depends on the specific observatory, right? So just to give you a sense, what is the exposure time for ZTF? Anybody know this? The exposure time for ZTF? Thank you. 30 seconds. Anybody know what is the overhead time for ZTF? How much time does ZTF waste between two exposures? Yeah, it's about okay. According to Eric's paper, it's 10.2 seconds. 10.2 seconds. Okay. And this is useful because oftentimes in survey literature, you will see what is called an observing efficiency. What that means is that observing efficiency means that if I was surveying one part of the sky, how much time am I actually using to expose on the sky relative to the total time that I'm spending? And that is just T exposure divided by T exposure plus the overhead, which for the case of ZTF is about 66%. No, sorry, 75%. So 75% is actually a fairly good number. It means that if I was observing 10 hours in a night, 7.5 hours of those time is actually being used to collect photons from the sky, which is good. I'm not wasting that much time doing other things. For LSST, anybody know the exposure time? And we'll get to why it is for whatever it is for LSST. But
Can you just say 15 seconds?
yes, so LSST is actually 2 times 15 seconds. It takes 2 15-second exposures. And the overhead that I have from the latest published numbers from the document is 12.2 seconds. It might be slightly different depending on what they figured out in the commissioning. But there again, you see the observing efficiency is about somewhat very similar to ZTF, whatever, 70% or something.
Don't you have a readout also between the two exposures?
Between the two exposures. Sorry, you mean between?
Like you said, it's 2 times 15-second exposures.
Yes, this overhead includes everything. Yes,
Okay.
yes, yes. So it is it's impressive in the sense that it is not only the largest camera, but it also reads out almost equally fast. So it's all a technological miracle in many ways. Okay, we're getting there. Okay, so good. We have basically everything we need to formalize what is the number of gallons per minute for our survey. Sorry, I just love this unit, gallons per minute. It's a very, yes, yeah, yes. Yes, sorry, yes.
Is there a way to account for weather other than just like an uptime? Like if you're doing something where you're seeing like CTIO is having a lot of bad weather right now, like is it anything more than just this % of nights are usable?
Oh, so this is assuming that weather stuff is not playing a role. Like if the conditions were perfectly clear.
Yeah.
Yes. So this is in perfectly clear conditions. LSST would be exposing on sky for 70 to 75% of the time. But yes, there will always be weather losses. Sorry, was that your question?
Well, I was asking, when do you account for weather losses? Is it is there a cleverer way to account for weather losses other than just this percentage of my nights are usable? Like if I was looking at the cost of, say, putting a telescope in here in New York versus putting it in in the Atacama Desert.
Yes. Right. So I think this is more of a sort of statistical weather averages, which is that, I don't think it would be a sensible decision to put telescope anywhere in New York.
Yes.
Right. So I think those, memory is that I think where LSST is, there are about 300 usable nights every year out of the 365.
Or so people
Yes.
just use the fraction.
Yeah, yes, yes, yes. It's kind of hard to predict whether we can predict this exactly. Weather is much more unpredictable. Okay. All right, we have all the formal setup that we need. So then this is the amount of volume that we're probing in our exposure, which scales as t to the 3/4. And this is the amount of time it takes me to get that volume. Correct? So the number of gallons per minute is, let's call it V dot, which is the amount of volume I'm probing per unit time. This is omega FOV divided by 4 pi times 4 pi by 3 dV cube divided by T exposure plus DOH. The amount of volume that we're probing divided by the amount of time that it takes us to get that data. Okay? And all of these prefactors are not that important. The main thing we want to see is that if you look at what the time dependence of this equation is, the numerator is proportional to t to the 3/4, and the denominator is proportional to t plus TOH, right? So this term is t to the 3/4 divided by t, let's call it t plus TOH. Okay, that's it. This is what tells me how fast is my survey when it comes to probing a certain amount of volume in the universe. So given this, should we take super long exposures or super short exposures and do multiple exposures? How does this behave as a function of time? Let's take the two limits. Okay, let's say when t is much smaller than TOH, in this limit, this becomes, this is, you can ignore this, goes as t to the, wait, am I getting this right? Sorry, t, let's say t is, right. If t is much bigger than the overhead time, then I can ignore the overhead entirely, right? So this becomes t to the 3/4 divided by t. This goes as t to the minus 1/4, right? Which means that if I take super long exposures, then the amount of volume that I'm probing actually is going down with time. And this is effectively saying is that because the volume that you're probing with a given exposure only increases as 3/4, whereas the amount of time you're spending scales as linearly with t, it means that you're effectively losing if you take super duper long exposures. Okay? See the other limit where TOH is much greater than t, which means that I can ignore this term in the denominator, and then this is proportional to t to the 3/4. So it's increasing when my exposure time is super short. So our mean value theorem would tell us that if it's increasing at short exposure times and decreasing at very long exposure times, there must be a peak somewhere. There is a peak in exposure time where you get the maximum volumetric speed for a given survey. Okay, now people start getting why 15 seconds, 30 seconds for exposure. So I'll show you a plot from Eric Bell's paper from a few years ago, which shows you exactly this. So, sorry, let me go. Oops, sorry. All right. So these are simulations that Eric did. It's not a simulation, it's just an analytical equation for that matter. What you see here is the volumetric speed of, I think this is ZTF, for two different overhead times. One is 15 seconds, one is 30 seconds. What you see is that when you have very small exposure times, as you keep increasing the exposure time, the amount of the volumetric speed increases, but then it plateaus out and then it starts dropping. And that's for two different curves of overhead times for 15 seconds and 30 seconds. what you see is that as the overhead of the survey increases, it peaks at a later exposure time and the overall thing drops. Which means that in order to make an effective survey, I want my overhead times to be small. See, so the peak volumetric speed is higher for shorter exposure time, for shorter overhead times. And the reason I'm showing this is because this answers the question that I started out with at the start, which is why aren't we using our, just take an 8-meter telescope, Subaru, which has these big cameras, or these surveys like, the Blanco telescope. Why aren't we as impressed with these? Is because LSST is designed to have small overhead times. You cannot do a survey with a telescope which has a large overhead time. And for traditional 8-meter, 10-meter telescopes, they take very long times to slew because these are gigantic structures. And one of the technological innovations of what makes LSST what it is the fact that it can slew. So just to convince you of that, I actually put this video in, which hopefully runs. This is from the Rubin website, which shows how quickly the telescope actually moves. So I believe this is a real-time animation. What you see here is how quickly the telescope, it's a gigantic structure, but yet it is able to move very quickly between fields. And that's one of the big innovations of having a telescope that is not only big, but also has very short overhead between exposures, because it can move so quickly and read out so quickly. Yes.
Does Rubin use a guide star or anything to that effect, or is it entirely just pointed by mechanical position?
Igor would know this question. You know the answer to this question better? I have some idea, but I'm not sure.
I think it's just mechanical position. At the end of the day, you need to be close enough to the field where you want to be, and then be able to track regularly. I don't think they use a guiding system, although they have also the auxiliary telescope to help with calibration as well.
Yes.
So everything will be complete.
Right.
Can I actually ask a question?
Yes.
My understanding is that every time you do a readout,
Yes.
you also add some noise term, the readout noise.
Yeah.
Is that negligible in the modern CCDs, or how does that affect the curve?
Right. So so what we assumed was that for very faint sources, the noise term is dominated by the Poisson noise from the sky. That's what we assumed. But yes, so usually for modern CCDs, the readout noise is not a dominant noise budget. So right. So I think one exposure or two exposures is fine, but I think there are situations, especially in infrared detectors, where the readout noise can become a problem, in which you have to keep reading out again and again and again. But for optical CCDs, this is largely not an issue. Yes. Okay. Any questions so far? Yes.
What's readout noise?
Okay, sorry. So readout noise is, so let's say that I have my detector at basically a constant state, nothing is changing, and I keep reading out the detector again and again. In an ideal world, you would expect that I would get the exact same values every time, right? Because the CCD is the same, there is no external change in factors. Turns out that that's not true in real life. Every time you read out the detector, you get a slightly different value, and the spread of those values is what we call a readout noise. Just because, it's a property of the electronic readout system, which it's specific to every detector. Okay. Yes.
So like in an ideal world where,
Yes.
let's say you get your overhead time really tiny for some reason.
Yes.
There's still like a practical reason to have like long exposures if you want to like see like a faint target.
Yes.
And then like, you also don't want arbitrarily long exposures where you're going to saturate. So like, how does that affect this curve?
So so something that we've ignored in this talk is like things like saturation, that every detector has a finite level at which it becomes, well, after that photon count, you stop being sensitive to more photons. So so we haven't accounted for that. So I think what ends up happening is that this effectively ends up deciding what my survey volume footprint is. So the example I like to give is that, where's my, so I'm gonna grab this. So if you take an instrument like HST or JWST, and let's say I magically got time on it to do a survey, then if you think of try to visualize the volume of the universe that you're probing with a survey like with what you would do with JWST compared to ZTF or LSST. So let's say we are an observer over here. This is the volume of the universe. For an HST survey, which actually has been done, everybody heard of the Nobel Prize in Type 1a supernovae? That used HST as a survey machine to look at very, very high redshift Type 1a supernovae. So if you think of the volume that a survey is probing, an instrument like HST the volume looks something like this. It's a narrow pencil beam on the sky. And you're detecting every supernova that's going on in this volume. For a survey like ZTF or LSST, the volume looks like this. Everybody is able to visualize what this is. So this actually brings us to another common terminology you'll see in survey literature. This is what we call a pencil beam survey because it looks like a pencil. This is what we call a synoptic survey because it covers a large footprint on the sky. So again, it's decided ultimately by your survey goals. If I was interested in finding high redshift Type 1a supernovae, I would not use ZTF. It's not the right instrument. But if I want to find specifically supernovae at very high redshifts, I would just do this. Take HST, which has a narrow field of view, about maybe 10 square arc minutes. This is what I would get. And this makes me very good at finding things that are very, very far away. So it's ultimately a choice of survey design. Okay. Yes.
There's also this point when you discuss surveys that go with very high redshift and also this Euclidean geometry.
Yeah.
We haven't.
Yes. We haven't talked about cosmological effects and so on. This is more of a simplistic view of it. Okay.
So
yes.
Is this one?
Yes, it's synoptic in some sense. Well, depends on who you ask, but I think ZTF is a better example of something that's really wide field and nearby. LSST is somewhere in the middle of these things, I would argue, because it is deeper, but it still has a wide field of view.
Is that one of the S's synoptic?
Yeah, well, so LSST used to be called the Large Synoptic Survey Telescope. Today it is called Legacy Survey of Space and Time. But again, like the original conception was Large Synoptic Survey Telescope, and obviously for these reasons. But again, yeah, synoptic in the sense that you can cover basically a big chunk of the sky at any given time. Okay. Yes.
Is there any reason you'd ever build something in between?
So again, I think it depends on who you ask. I would say LSST is in between with us because it does probe a very large volume in the universe. I think the sort of the nearby, the true synoptic version are things like Eviscope and ZTF and so on, which are like really wide field and are meant for very nearby sources. Okay. Yes.
This is a really dumb question.
Yes.
For the 1As with HST,
yes.
Did they go out to such high redshifts that they were actually looking in the infrared?
You mean whether the light for those 1As was shifted to the infrared? I think to some extent, yes, must be the case, yes. Which is why anybody hear of the Roman Space Telescope? This is what Roman is doing. Roman is doing this on an industrial scale. It's like a field of view which is 100 times the field of view of HST, which is still small compared to LSST. But what it's doing is exactly this. You have to go to the infrared for very far sources because the expansion of the universe moves all the optical light to the infrared. But that's one of the main drivers of Roman, which is that it does what HST does, except in the infrared, which is perfect for high redshift sources. And it is has a much bigger field of view than HST. Okay. Good. Let's see. I'm clearly not going to be able to cover everything I wanted, but that's fine. So which we can go over is, so far we've talked about a lot about how do you design a survey. These are some of the metrics that are commonly used. There are other metrics that are out there in the literature, and happy to chat about them. But this is one of the fundamental things. It's like he said, it's commonly referred to as a grasp or a volumetric speed of a survey. But I want to get to quickly touch over the second part of what makes a transient survey what it is, which is, let's say I have all of this set up ready. I can take images of the sky at very quick succession. How do I discover a transient in this data set? Like, how do I take an image of the sky, which is recorded on some sort of a CCD, and actually discover a transient on top of it? So I'm going to give you an exercise right now. Let's see. Sorry. Yes. So if you look back over there. So right. So how do we discover a transient? So what I'm showing here is that obviously the obvious fact that in order to discover a transient, you need to repeatedly look at the same part of the sky again and again. So here you see an image of some part of the sky. I'm not going to tell you what it is. And your exercise is that I'm going to flash another image right now, and I'm going to ask you to spot the transient in that. Okay, ready? Ready? 1, 2. Which is good. Yes. Okay, so hopefully it's obvious. What is the transient? Okay, the second level question is: does anybody know what transient that is? Take a wild guess. It's a supernova. Which one?
1A87.
Yes, this is 1980 supernova 1987A in the Magellanic Clouds. Yes. So right. So 1987A, I would say many would say is sort of really ushered in sort of many new eras of supernova physics in many ways. But what you see here, this is obviously something that's obvious. You can just look at it and say, oh, there's something that appeared, and this is a supernova. But this is how it used to happen historically back in the day. You had astronomers looking up in the sky and saying, oh, something appeared in the sky. And then you try to understand what it was. Of course, this is what used to happen. This was subsequently followed by an era of photographic plates. What I'm showing here are photographic plates from the Palomar Sky Survey. Anybody hear of Fritz Zwicky, the namesake for the Zwicky Transient Facility? Yes. So Fritz Zwicky had the privilege of discovering about, I think, 100 supernovae over 50 years or so, just by comparing photographic plates like that. Fortunately, we today live in an era where most of this is run with CCDs. Here are, I think, some of the most prolific ones that existed about 2 or 3 decades ago. Left, you see the Lick Observatory. This is Kate, which is one of the first robotic supernova surveys that existed. And what you see here is the focal plane, CCD focal plane for PTF, which was the predecessor for ZTF. So, all right. The reason I'm showing this is because I want to touch upon this technique, which I think is very close to my heart, and I think it's a fundamental way of sort of thinking about how to find transients, which is that let's say that I gave you 2 CCD images. This is, I took these images from one of my colleagues. These are images from the Palomar 60-inch telescope. And everybody see the galaxy in the image? Let's see if I can lower the light a bit. Yes. So hopefully you can see that there is a galaxy in that image. It's not very well reduced, but that's fine. We'll get to it. Right. So question is, here are 2 images of the sky that were taken some time apart. The left one is what I call a new image, which was taken more recently, and the right one is what I call a template, which means that it was taken some time ago. What the exercise that we are assigned is to find what has changed in between these 2 images to be able to discover a transient. What is the first order thing you could do? Sort of the simplest thing you could do with these 2 images to find if something has changed? Yes, good point. So what we can do is, the simplest thing you can do is subtract these 2 images. Turns out that, because these are digital images, we can now sort of do it quite easily on a computer. And this is what that plain subtraction looks like. Which is that, did the entire galaxy change in brightness at a given time? Like all the variable stars in the galaxy know about each other and they're coherently going up and down? Right? Yes, yes. So I wish we could discover physics like that, but I don't, yes, so that's not quite the case. Anybody know why this plane subtraction doesn't look nice?
There's some like astrometric error on there.
It's a good point. Astrometric error. What else? Was that? Yes, yes. So remember that both of, like I told you, these images are taken with the 16-inch telescope at Palomar, which is on the ground at a site which is it's like not that great of a site, which means that atmospheric effects are quite significant on ground-based telescopes, and for any given astronomical observation, you have your image of the sky that is being blurred by the turbulence in the atmosphere, which blurs out images. And you can almost see in this image, if you just compare the new image and the template image, you see the stars look slightly different sizes. All of that is because of atmospheric effects, which is why if you just went ahead and did a simple subtraction, this will not work, because even if every source in the star in the image was exactly the same brightness, they don't have the same shape anymore because of atmospheric effects. So how do we deal with this? All right, so that's going to be, we'll talk about for a bit, which is this idea of how image subtraction works. How do you correctly do image subtraction? So the first thing I want to highlight is that, does anybody actually have a sense of, do we actually resolve? So when you see an image of a star and you see some sort of profile on it, like it has some non-zero width, does that actually reflect the size of the star, like the physical size of the star? Okay, good, yes. So turns out the stars are, even though they are big in size, even resolving stars is impossible, nearly impossible for even the biggest and nearest stars. And it's only been done for maybe 2 or 3 stars, which are effectively the nearest red supergiants. They're tiny in terms of projected size on the sky, which means that basically all of these widths and profiles that you see, those are produced either with a combination, they're produced with a combination of optical diffraction effects in the telescope or atmospheric seeing effects, which we've talked about a bit over here. So if you wanted to mathematically formalize how this works, we said stars are effectively point sources in the sky. What is the mathematical description of a point source? So point spread function defines how a point is spread, right? So how do you mathematically define a point, a single point in a plane? Yes, thank you, delta function, yes. So if you plotted, let's say, flux as a function of position for a star in reality, what it looks like to a telescope, it basically looks like this. It's non-zero at one point and 0 everywhere else. This is what we call a delta function. So what does, let's say, the optics of the telescope or the atmosphere do to this delta function? What does it do? It spreads it out, right? Yes. So this profile goes from looking like that to looking like this is what we call the point spread function. And quite literally, it means this is how a point is spread. That's why it's called a point spread function. Okay. Oh, there's a mathematical term for this process. What is it called? Yes, thank you. So this is what we call a convolution. Okay, what that means is that you take a single point, you take a delta function, and you spread it out with some filter. This is what we call a convolution, right? So let's say this is the PSF of my telescope. Let's say I had a star, let's say any astronomical source that had a profile that looked like this. What would this look like after it got spread by the same point spread function? Just broadens out, right? Yeah, it's not. So yeah, so this would be a broader thing, right? So you're taking this. This is the convolution kernel effectively. and you're convolving this function with this. Okay. So in general, the point I'm getting at is that the recorded image that one gets out of a detector on a telescope is the, let's say, the true image of the sky, which we'll call S, convolved, and this is the symbol we'll use for convolution, convolved with the PSF of the device, of the optical system. Okay. Enough so far? Actually, maybe I should turn the lights back on. Sorry. So what that means is that the two images that you see on the presentation over there are actually have nothing to do, well, they have something to do with the actual image of the sky, but they are also severely impacted by what the convolution kernel is at the time of observation. So let's see our template image. Our template image is, let's say, whatever the sky looked like at the time of the reference image creation, convolved with the PSF at the time of the reference image creation. Similarly, my science image, let's not call it this, let's call it new image, maybe N. Yes. This is whatever the sky looked like at the time of the new image observation, convolved with the PSF at the time of the new image, when the new image was taken. And so when you subtract these two directly, what do you get? If I just do a plain subtraction like you see on the presentation over there, what you get is SR convolved, oops, sorry, this is the wrong way, N minus R. N minus R is SN times PN minus SR times PR, right? So yes, so you're not really quite seeing the change in the sky anymore. What you're seeing is a convolution of the actual change in the sky convolved with some strange convolution of what the observing conditions were at the time. Okay, so how do we deal with this? And this is actually like, this is a cottage industry of its own. Like, how do you do image subtraction correctly? Anybody know of heard how this happens? Yes.
You match the PSF.
Yes, yes. So if there was a magical way to, or well, hopefully a mathematical way of being able to remove these two different prefactors to the science and the reference image, I'm done, right? And this is, again, I would argue that this is not a solved problem. Like, there are groups around the world that are still spending day and night trying to figure out how to do image subtraction correctly. And everybody has their own favorite solution. Some of those are mathematically optimal for certain cases, some are not. But it's one of the things that is at the heart of any transient survey. Okay. So one really popular method that's been around, and you'll hear many terms for it. I think the original derivation was in Ibrahimovic. I forget the year of the paper, but this is what you'll commonly see, and this is actually what's used in ZTF, is this idea of a common PSF method. So what this says is that, I really need to get rid of the prefactors somehow. And what I'm going to do is to convolve the new image with the PSF of the reference image, and convolve the reference image with the PSF of the new image. What does that produce? So you get SN convolved with PN. I want to convolve this with the PSF of the reference image minus SR convolved with PR convolved with the PSF of the new image. Okay. So convolution, as we know, is a linear operation. It doesn't, the ordering of the thing doesn't really matter in these cases. So what you get eventually is that you can take this as a common factor that's out. What you get is SN minus SR. Remember that this is the term that we're interested in, which is what is the true difference in the sky images. And more importantly, this term, if zero, which is true for most sources in the sky. They're not like variable. Most sources in the sky are not highly variable. Then what you get is that if this term is 0, then this is just 0. Everything disappears. Okay. So this is what you'll commonly see in the literature referred to as a common PSF method. And it's very popularly implemented in this technique that's called Zogi. Anybody heard of Zogi? The method. So this is how Zogi works. It brings both the science image and the reference image to a common PSF. In this case, this is what we call the difference image, and this is the PSF of the difference image. So just to convince you that I wasn't really lying about all of this, if you just go back and look at your screen, yes, so this is what we already saw. What the PSF is doing is effectively you're doing a convolution, which is taking your filter and then moving it across the true image of the sky. So the top animation shows you how this filter is slowly moving across the image of the sky. And what you end up getting is this weird triangular thing that comes out as the output of this convolution process. And if I actually do just this common PSF method applied to this data, nothing else, just simply this, nothing else, to that previous image that we saw. These are the two images. Everybody see something changed between the two images? I will turn off the light. Yes. Everybody see the supernova? It's slightly offset, and you see there is a slight residual right next to the supernova. This is what we, I think you, Brian, you mentioned this astrometric residual. So you see that slightly on the nucleus. That's again has to do with the perfectness of the reduction. But what you see is that instead of seeing that horrible image that didn't give us any information about whether the sky changed, you do this process, you bring the two images to a common PSF, and you start discovering things. Now, this is, of course, a very simplistic view of doing it. Turns out that there is, I think, a 25-page paper on Zogi, which tells you how the mathematics of this works, why this is the optimal way of doing it. And of course, we will not have a time to actually go through that. But this is what all that mathematics looks like. What you see in the top left is what is defined as the optimal difference image. Now, what you see here is that instead of convolutions, you see multiplications of the PSFs of the images. And that's because of the simple theorem that a convolution in the spatial domain is what? In the Fourier domain, what is it? If you do a convolution in space, if you take it to frequency, it becomes a product, yes. So most of these methods actually work in Fourier space because computers are very good at doing fast Fourier transforms. It's just very effective. So what you see in the Zogi paper is that most of this mathematics is actually derived in Fourier space, which is that if you take two images, if you want to convolve them, then the easiest way to do it is to take the Fourier transform of both of those images, multiply the products in Fourier space, and then just reconvert it back into real space. So that's what this difference image is. The bottom is what is called the score image. Again, not going into the details, but that turns out that Zogi has certain nice properties that allows you to quantify the statistical significance of whether this thing that I see in the image, is that a 5 sigma detection, is that a 10 sigma detection, 100 sigma detection. Turns out that there's some very nice mathematical properties that allow you to do that. Now, that being said, I will say that it's not a perfect method. There are regimes where it breaks down, and this is stuff that keeps me awake at night. I spend a lot of time thinking about how do I modify this equation to work in cases that it was not meant to work in. And that's, I think, one of the frontiers of sort of image processing techniques in astronomy today. It's going to be very relevant for LSST definitely, and particularly for Roman, because it turns out that this equation does not behave very nicely when you have very dense crowded fields, and you have one star in every pixel of the sky, which is going to be the case when you're using LSST to look into the galactic bulge, for example, or if you're using Roman to look into the galactic bulge. Turns out that some of these assumptions do not quite hold, and that's like active frontier for research today. All right, any questions about this so far? I think otherwise I'm done. I think this is a good point to stop. Yes.
This is going way back.
Yes.
Why 2 15-second exposures for ribbon and not 1 30-second?
Yes. So Igor will probably talk about it today, but it's to detect fast changing things. Is that right? Did I say that correctly?
That's another question. I have a slide for you guys to think about.
Okay, good.
it
Yes.
and,
Okay, good.
discuss.
Yes.
So
I gave the answer.
let's
Sorry.
pick it up
Yeah.
in about half an hour.
Yes. Okay. Any questions? Yes.
So usually it seems like people do photometry on the difference image
Yes.
with the convolved point spread functions
Mhm.
from both of them. If you know the convolved point spread function,
Yes.
why don't people just back it out to a skyfold delta functions and try to do photometry on the skyfold delta functions?
Because there is no new information in that. Like the amount of information that we get is ultimately limited to this. You could do your fancy thing of recreating a sky full of delta function, but it's exactly the same information content as this. Yes. Because ultimately the atmosphere limits the amount of information we get. Like you could have, let's say, a supernova with another supernova right next to it, within 0.1 pixels, but you would never know. It's impossible because it's ultimately blurred to us. So the information content does not change. Yes.
Do you run into a problem if your field of view is big enough where the PSF changes
Yes.
across the field of view?
That's a problem. Yes. Turns out there are some variations of this Zogi method for people who are in this literature. It's called SFFT. It's called the Saccadic fast Fourier transform, whatever is it called? Yeah, right. Yes. That turns out that there are ways to implement Zogi in a way that accounts for these PSF variations. The other simple way, which actually the way ZTF does it, is that you divide up the image into multiple chunks instead of doing a full 47 square degrees, and you individually compute a PSF for every chunk and then apply Zogi. But there are ways there is a continuous version of that, which is implemented in. There is this funny image subtraction algorithm. I don't know if everyone knows it. It's called hot pants. Everybody heard of hot pants? Hot pants is higher order transform of PSF and template subtraction. Yes, it's one of those popular codes that's been around, but that implements some variation of that.
If you do the version where you divide it up, what do you need in each? Like, do you need like well separated stars in each?
Yeah, you
chunk?
need enough stars in every divided quadrant. Every divided section to be able to derive a PSF model.
So you couldn't have one that was just like the galaxy that you showed. Like you could not do.
Oh no.
PSF.
You would need some isolated point sources to be able to derive a PSF, and that's again one of the challenges in galactic bulge fields, which is that there is no source that is isolated in a galactic bulge field. And that makes it challenging. Yes.
Wait, so the issue you run into the black bulge is that you can't measure the PSF, or you can't deconvolve the PSF even if you know it because stars are so close together.
So I think you can measure the PSF if you take sufficiently bright sources, because for bright sources, the nearby sources are not a big contamination. I think the challenge you end up getting is that how do I measure the noise in the image? When the way you measure noise in images is that you want some pixels that do not have sources in them. That gives you a sense of what the intrinsic noise per pixel is. In the galactic bulge, there is no pixel that doesn't have a star in it. So you're always limited by confusion noise. And that becomes a challenge. And it's like, we've tried things like forward modeling and all that, but it's a difficult problem. It's going to be very relevant for both LSST and Roman once you get to this thing. So anyway, I will my intention was to stop by showing you this slide to set Igor up for his thing. But anyway, you will see a lot of this, you will see a lot of choices that have been made for LSST. And the hope for this talk was to really give you a sense of, how do you take your telescope? I have a fancy new telescope, and how do I design a survey out of it that maximizes certain things that I'm interested in? Okay, all right, let's go for coffee break. Thank you. Okay, so we'll get started. So it's a pleasure to have Igor Andreoni over here. Igor got his undergrad degree from Milan and then was a PhD student at Swinburne, was a postdoc at Caltech and University of Maryland, and then since then has been a professor at University of North Carolina in Chapel Hill. So Igor works on a lot of the fast transient searches that we've been hearing of at this school. He's served as the co-chair of the Transients and Variable Science collaboration of LSST. And today he'll be telling us about what LSST, what the actual numbers of LSST are all about. So.
Thank you, Kishalay. Thank you all for being here. Looks like CCA wants me to remind you all, yes, I'm Italian. I'm actually holding a small, very small coffee cup. Yes. And yeah, I was thinking today, I would start really just by telling you, well, a lot of things you already know, but it's fine. We breeze through a little bit of history of service, because I think it's important to remind ourselves, how did we even get here? I would like to spend a couple of words talking about Vera Rubin, the person and scientist, not just as an observatory. After that, we will dig in what the latest is in terms of survey strategy. So you always have to keep at the back of your mind all you've learned from Kishalay this morning when kind of giving a look and try to assess all the maps of the sky that you will see that will tell you what the plans are for surveying the sky with LSST. I will conclude with a bit of data access, and if there is time, I will make a brief mention to the Argus array, which is, I think a lot of you will get excited about this new instrument that should come online in 2-3 years. I'm looking at John because he's part of the Argus team.
Our official public statement is we were aiming for commissioning or first slide, 2027-ish.
2027. Okay. Before that, okay, let's start extremely basic. Who consider themselves a big fan of Big Bang Theory? Wow. Nobody. Who has watched at least one episode? Okay, then that's right. I'm not a big fan, but you know, it's nice when you're on the plane, typically, or you're about to land, you don't have time for a full movie. But maybe some of you have stumbled upon like a scene in which Sheldon is to explain to Penny, she wants to learn about physics, and he goes all the way back. Now, we're not going to do that literally, but I think it's important to remember, where did we start studying transients? Anything that was changing in the sky in ancient times was considered scary. The portent of doom. I think the first transient ever observed was really the moon. It's something that breaks the paradigm of perfection of the night sky. And if you look at our more like Western culture, probably you're familiar, more or less, about work by David Fabricius, Herschel, pioneers in the study of the variable sky. However, maybe not all of you know, I would expect at least one of you to know that in the land down under, people have been familiar with the variable sky for thousands of years. Observations were made by eye, and the knowledge was carried from one generation to the next, just with oral culture. And again, that's something I think, keep in mind, this is how far we've come from. And let's value just really how incredible observers we've had in the history of humanity. First transient, more like in terms of supernovae that was ever recorded, again, it's dating thousands of years ago. This is beautiful. This graffiti were found, I think, in the Kashmir region, India, Pakistan. I'm not super familiar with the geography, but that's probably the first written recording of a supernova. And then, of course, we have the plates, like photography plates, like Kishalay told us. Now we have detectors that allow for more automation. You can see transients with image subtraction. I will not go through all of that, even if I did basically a whole PhD on it. This has been a lot of fun. But also, again, we came from a time in which Zwicky, already mentioned, observed galaxies in a targeted manner and visually look for transients. And then you have people who really love doing that and found, I think, more than 100 supernovae this way from their backyard. And also, I think a lot of you probably will want to keep doing astronomy for the rest of your life, you will receive a lot of email from nutcases. That's fine. But you will also receive sometimes email from amateur astronomers. I encourage you to give them some credit, some look. In some cases, data acquired by amateur astronomers made a paper worthy, let's say, of a very high impact factor publication. Well, sorry, a publication of very high impact factor journal. Like in this case, in which an amateur astronomer was observing a nearby galaxy with a lot of short observations and ended up finding, I think, the most rapid rise ever observed in the optical, at least at the time, for a supernova. So the shock breakout following the core collapse. The optical wide field survey, as we like and love them nowadays, according to Shri Kulkarni, who's been a mentor to Kishalay, myself, and I think maybe a few others in the room, this modern era really started with Zwicky and Bade, and it's all about cadence, a controlled experiment. You need kind of to know what you want to do, to give yourself room to study well what you want to study, and also to study the unknown in a way that you can control, that you can understand, you can do physics and astrophysics with. And you didn't show this, Kishalay, but so when he was at Caltech as a student, he deployed the Gattini IR survey you mentioned before. I don't know if this video is from the telescope or is the rooftop of the building. That's Palomar. Yeah, you don't see any star from Pasadena. That's fine. But I mean, this is a modern survey, fully roboticized, data acquired in an automatic manner, transfer. You have a very dedicated PhD student that will do image subtraction, deliver transients for you. And now we'll see how we can bring that to scale, really. Rubin is all about scale, pretty much. And let's not forget also that other surveys are active now and will hopefully keep being active for a few more years to come. And I imagine, yeah, many of you have worked at least with this or that instrument. I apologize in case your favorite one is not in the slide. These are just a handful of those most active in the last 10 years or so. What they're typically characterized by are multiple filters. Some systems work with maybe just clear filter to get as many photons as possible. You don't want to block off any type of light, but filters help. Knowing the color of what you're observing gives a direct link to the temperature, possibly inferring immediately when combined with the rest of the light curve, what you're dealing with, astrophysically speaking. Aperture size of modern survey tends to be not too large. The large telescopes are extremely expensive, hard to make, take a 10, 20-year time scale to produce a project that is more than, say, 2-meter class. And the field of view is truly been the frontier for a long time. And Rubin is kind of reverting back in that. It's a wide field of view, but not quite as ZTF or Assassin or others. But yeah, a lot of gallons of sky. That's what Rubin is going to aim for. Probably all of you are already familiar with ZTF at Palomar. I think it's nice to also keep in mind the size of the focal plane is no joke. This is Roger Smith, the chief engineer. He's a nice bloke from Australia as well, lovely accent, and really, really tall guy. And this is important because for the scale, like the filter is probably, if it was me, it would be like this, I think. It's huge. And Rubin, again, is going to be the biggest camera ever built. Actually, I have a photo. I unfortunately didn't put it here. There is a person fitting in the slot for the filters of Rubin. And all of you have seen this image so many times. I will skip through, but actually something to notice is the limiting magnitude. Thank you, Kishalay, for talking about fluxes, which are more physical units, but we don't like flux. I will not talk about fluxes at all. I will talk about magnitudes. This kind of pseudo log scale system. We like to put a number for each survey just to compare and contrast. So for ZTF, about 20.5, depending on lunation, goes from maybe 19.5 to 21 when conditions are really good. And I think a lot of you work with ZTF alerts. Has anyone ever downloaded a full frame image? Who has ever downloaded a ZTF full frame image? Not many, but it's fine. But I understand that. Just encourage you to do that at least once. See what the data look like. For example, in this case, this is a bit cheating. This is not like anywhere in the sky. This is fairly close to the galactic plane. It's a field where a fast radio burst went off. We observed the host galaxy that, of course, nowadays, all the exciting transients are behind the galactic plane. I don't know. There's something wrong about the universe. But you can tell how many stars are in the foreground, even in that little square. Now, for whoever downloaded it, is this a full frame image? It's not. What do you think this is, just from a quick look, if I can put you on the spot for that?
It's one of the detectors. I think there's like 15 or 20 of them. I actually don't know.
Yeah, so there are 16 detectors. This is one quadrant of a detector. So 1 part in 4. So there are 64 of these in every ZTF image. And this is a small survey compared to Rubin. That's why we talk big data. That's something I think we have to remind ourselves that we should appreciate, also to know all the work that is going on behind the scenes. So Rubin is built. This is all real photos. We have real data now. I'll show some in a moment. The nominal magnitudes, they keep varying depending on the throughput of the filter they choose, of the type of aluminum they put on the mirror, on the exposure times. What do we do? 2 exposure to 15 seconds or 130? But 24 point something, I think 24.5 maybe it's even a more updated value for the R-band standard 30-second exposure. Now, if you're very smart, you do all the calculations. If you're even smarter, use AstroPy to calculate the co-moving volume, which is more accurate than the approximation for type 1a supernovae. It's nice how many things we thought of presenting the same way. So what's the difference in volume? What's the ratio in volume that Rubin will achieve compared to ZTF, for example? Well, again, just throw in the numbers, pick a certain magnitude that you want to reach, absolute magnitude, so minus 19 or so for supernovae. Nabil, do you agree? Minus 19.5-ish, yeah, that's fine. Then you can tell, okay, this is the volume you can probe. And I found it curious that the ratio between the co-moving volume that you can probe for type 1a supernova with Rubin over the same value for ZTF is 9.6. And 9.6 is exactly the field of view of Rubin. I think there is some cosmologists here playing numerology Kabbalah stuff. Before digging in the survey, once again, let's not forget, Rubin Observatory changed its name also, I'll show in a minute, to honor the person, the scientist of Vera Rubin. This is a picture that was stored in the archives of, I think it was Carnegie Institution, yeah, of Vera Rubin, very young, working on the instruments, although her work has not been quite, like, the reason why she's so famous is not quite because of instrumentation, but more data acquisition, data analysis. What did she do? who has ever heard about Vera Rubin outside the fact that it's an observatory? Okay, that's pretty good. First word that comes to mind talking about Vera Rubin scientifically. Dark matter, of course. Looks like you're all familiar with it, so just very quickly through it. She studied rotation curves of galaxies. Now, if you assume a Keplerian situation, the expectation is that the rotational velocity would decrease this exponential curve as you move out from the nucleus of the galaxy outside the halo. That's not what was observed. What was observed is that as you keep progressing in distance, the curves remain flat. That's not okay. That's not how physics should work, unless you have extra mass. And that's the most conclusive proof we, I think, still have nowadays of the existence of some dark matter that, as all of you know, we call dark because we have no idea what it is. So for this reason of honoring the scientists and also honoring the person as an advocate for women in science, there has been this consensus of using the full name of Vera Rubin when referring to the observatory. So in your publication, you can maybe spell out the name at the very beginning and then just call it Rubin moving forward. If you need, to be a little bit compact, you want to write Vera C. Rubin Observatory every time. That's gonna be a lot of ink if you ever have the interesting idea of printing out your paper. Just stay away from VRO. A lot of people do that because that's what we do in astronomy. We put an acronym on everything. Please just don't do that for this observatory. And hopefully this practice, I think, will be also carried on to other observatories as well. There are 4 main science pillars at the foundation of Rubin. I actually should have put a picture of him as well, of the person, kind of the father of Rubin Observatory. A lot of people were talking about it at the Rubin Community Workshop last week in Tucson. That's why I was not around yet. I was at this meeting. A lot of people, especially more the older generation, you kind of, the stereotype has to be a little bit grumpy about things. Like the new generation thinks that a project like Rubin comes out of nothing, out of nowhere. It just appears. No, it takes a lot of time, a lot of writing proposals, a lot of convincing agencies. You also need the person or the group of people at the beginning that have the vision for it. So the vision, in this case of Tony Tyson, again, I regret, sorry for not putting the picture of Tony's. Maybe you can Google him up, and hopefully many of you has already had a chance to meet him or will have a chance to meet him in the future. But those pillars are studied the Milky Way structure and its formation, have a census of the solar system like never before, studied the dark energy, dark matter, everything dark, and the changing sky. Let me see 1 second. Yes. So the idea here is to have one survey that would allow you to tap into all these science cases as well as you can. Although that's such a difficult optimization process. I'll talk about it basically for the rest of this lecture. The question I have for you that was half stolen by Kishalay: what do you need to observe to tap in this science field, to tackle the science questions? And how? What do you need from a technical standpoint? Can I please have you pair up, spend a couple of minutes talking with your neighbor about all of this? You will not be quizzed, but it's good to think about it. Do you need like static images? You need series of images? What do you need? How good your photometry does have to be. Go.
You're the right person.
Love it. All right, let's bring it in. So how about, without going too much in detail, we bring up maybe one point of what to observe and how for each of the theme. What about the Milky Way structure information? I'll volunteer for what do we want to observe? One person, please.
Like we want to see like different like stellar streams and like the like how the history of like the galaxy was potentially formed, I think. So lots of stars kind of in the outside, deeper or fainter like galactic sources that we haven't seen.
Excellent. I think a lot of stars, that's pretty much what my answer would have been too. And maybe from someone else, what do you need to be able to achieve that?
Well, like really deep photometry.
Yes. Correct, for sure. Anything else?
IR.
Maybe, yeah, be sensitive in the IR.
A lot of dust.
Excellent. I like these ideas that are coming up. Anything?
Good astrometry and proper motions.
Fantastic. So you need all these elements to come together to achieve this in a sensible manner. What about the solar system census? Asteroids, rocks.
Maybe you need a good cadence because presumably you're tracking the motions in the sky, but
Mhm.
then they're also faint.
Yep, correct.
Do you want like a really, really wide footprint? Like you want really as big an area of the sky as you possibly can because it's everywhere.
Yeah, right. You want to observe a lot of the sky, and I will add, you also want to observe maybe mainly the ecliptic. So maybe putting the telescope at the South Pole may not be the best idea for the science case, given the limitations in declination, right? It's always like a trade-off with a lot of other things. What about dark matter and dark energy?
You want that full 10-year, really deep data set.
Mm-hmm. To observe what? What would your target be?
Galaxies.
Galaxies, of course. Anything else?
Lots of filters for good photoses.
Good photosys. So you want to know also the distance, even if you cannot go as deep with spectroscopy. That's really hard to do. Anything else? Even cosmologists like transients sometimes. Which transients do they like? Type 1As. Well, and also gravitational wave counterparts. We can use them also as standard sirens. Finally, the changing sky, the one a bit closer to my own mic and my own heart. What do we need? Well, sorry, first of all, what do you want to observe? Just shoot names of some trains that you really like. What?
Tidal disruption events.
I heard something from there.
Luminous red novae.
Luminous red novae. What do we need?
High cadence.
Cadence. It's all about the cadence. You will not be surprised. I will actually show a slide with all the papers that we wrote to basically tell observatory, can you please improve the cadence? Which was pretty bad to start with. One more note about the camera. Has anyone ever been? I've never been here. Has anyone ever been to a show at the Sphere in Vegas? Yes. You have. So now we know where to organize the next school. Can we tell you? It's just a few $1 million.
Rubin images of the Sphere.
Did they do that for the first look party? They should next time. The Sphere. So the claim is that the Sphere can display any image in the world, and that's grossly incorrect. What was the number of megapixel that Rubin will have? You deleted it. Billions, and here you have only 57.6 million pixels in the Sphere. So you will only be able to project, I think, what part in what? 17, I think, if I remember correctly, like a small fraction of a Rubin image on the Sphere. And this is what almost every point in the southern sky is going to look like. This is after a 10-year survey. Images are co-added together. Kishalay talked a lot about the theory behind image subtraction, but similar arguments can be made, similar algorithm can be developed for the optimal stacking of images. So combining observation in a manner that really allows you to maximize depth. So imagine all the southern hemisphere and a little bit of the equatorial regions looking like this, with photosys, like John mentioned, and in addition, information about the dynamic sky. Field of view, 9.6 square degrees, 6 filters from almost UV, U band, all the way to Y band. So tapping a little bit in the near infrared, as we want to do, for example, for stellar science. We talked a lot about resolution already, good pixel scale, good seeing, and adaptive optics. You have the activators that will change the shape of the mirrors to basically counterbalance the effects of the turbulence of the atmosphere. We will have such good resolution. This, once again, is good. I know that this is a little bit public lecture sort of thing, but it's okay. I think we all need to be a bit grounded, not feel, too cocky with the fact that we do big data now. Just think about it. If you fly 15 miles high and you manage to spot a golf ball and resolve 2 golf balls next to each other, that you're Rubin at that point. That's how good the instrument is. Why it's there, I have no idea. So let's talk about survey strategy. Well, first of all, before I move on, are there any questions so far? If not, let's get a little bit more in depth. So the survey strategy definition has been a iterative community process. So there is iteration between community input, then people from the project take this input and carry out simulation. The software is called OpSim. Probably a lot of you are familiar with it. I think it's one of the best survey simulation software ever coded, also because it's been developed over so many years by now. So the idea is they recreate they do create something that doesn't exist yet, which is the survey that Rubin will carry out, taking into account how the scheduler will operate, which is now an AI decision-powered scheduler. They call it an intelligent scheduler. I don't know what if you're religious or what, but hopefully it will deliver something really unprecedented thanks to the help of AI. It's gonna be okay. Robots are taking over, and we know that. That's fine. So thanks to this OpSim, people can design what we call metrics, basically snippets, pieces of Python code that will yield a sort of, allow us to quantify how well we can achieve a science goal. For example, if you like type 1a supernova, your metric could be if I inject light curves of type 1a supernova in my data, how many can I recover? What fraction can I recover? 100% will be 1. 50% will be 0.5. What if I change the way that the scheduler works? If I change the cadence? Well, maybe it goes up, maybe it goes down. And thanks to all these metrics, there's been a process, these iterations between the project and the community to keep improving. Other surveys like ZTF, especially at the beginning, I think has been a much more tyrannic sort of, like, I think it was the PI who said, this is how we're gonna do it, period. It was definitely more efficient because making people agree is hard. And if you're in an environment like Rubin, the community is at the heart of it. It's not just technology. And dealing, with your peers, it's not always the easiest thing, especially if your interests are in contrast with each other. If someone is interested in galactic plane and I like extragalactic transients, we have a problem. So that's what we have to always balance. So for example, cosmologists, to be able to study dark energy, they want a very uniform coverage of the sky. Their observations are not uniform. It's hard for them to do their science. But for me, the study transit, I don't care. I just want high cadence or certain filters. How can we agree? The kind of motto of Rubin, I think, was Zeljko Ivesic, the director, who came up with, we're not trying to maximize happiness. We're trying to minimize unhappiness. So a lot of people are unhappy, but minimally so. The person who has been kind of in charge of this process on various levels is Federica Bianco. In fact, later I will use a bunch of slides from her latest updates from last week. So what you're gonna hear is really the very latest on the project. She's a professor at the University of Delaware, deputy project scientist for Rubin. But if you need any more inspiration, she's also pretty well known to be a public figure in boxing. She has been for a while both a professional astronomer and a professional boxer. So, interesting person to know. don't cross her. I've never tried, but yeah. And she has led a paper that I encourage you all to give a look at that explains this process and opens this issue on APJ supplements for all the Rubin survey cadence publications. There is a committee that was instituted to be able to evaluate all the feedback from the people. So people like you all are asked, provide us with metrics. Tell us how well this or that cadence is doing. And this committee will then take all the results, evaluate them, and basically decide on which improvements are needed in these iterations. I think you recognize a lot of the people up there. They're typically well-established professor researchers in general. So we really need a lot of experience and awareness of the science to make sure this process is done in the best way. This is where we started from in 2018. How about we take one more minute for you to once again work in pair and discuss the problems with this map. Before you start, let's agree on what we're looking at. Oval is the sky. As you get from blue to yellow, that's you have an increasing number of visits. So yellow places, yellow spots are very high number of visits, and the other ones very little. Give it a thought. Talk about it. Go.
Yes.
I thought the goal was a layer.
Sorry, my galaxy and our galaxy.
In this rendering, is the
I just tried
No, I think the bulge is somewhere here. What are the coordinates of Sagittarius star? Total. All bands. All right. So problems. Give me problems. Any volunteer to give problems?
across most of the sky, you're getting, if there's only two filters, so if you're doing ZTF, you get 2 or 3 data points for a 1A rising in the low cadence Alder regions, which might not be enough to pick it up.
Okay, so if I can rephrase what you're saying is that the total number of visits may not be quite enough to have high cadence in all the 6 filters you're planning to, because this is all bands. This is what you're looking at. Visits in any band, really. Other issues?
No galaxy or no Milky Way.
There is no Milky Way, or very little Milky Way. So it's probably here-ish. Yeah, that's a problem. What else? Not for me, but for Kishalay. Any other issues?
Very southern.
Yes. I don't think in our power to move the telescope north, however.
But like basically the like you maybe want the deeper, like you want to be able to follow up.
Yeah. So that's actually a problem that was addressed even before the definition of this survey. You see this area here. It was actually an addition to the main survey, exactly to be able to go somewhat north as much as possible, primarily for solar system object science, because that's you have the ecliptic here. Also, let me add, it's very south, but it's also very north. You don't have good observations of the South Pole Cup, which may be a problem. I mean, this is the region where you may have even better cadence potentially, right? And I'm pretty sure there are interesting cluster and other objects down there. So long story short, there is a lot of work to do.
But, sorry, why don't you have good observations of the southern pole if the telescope is in the south?
I don't know. I am not sure. I think to some extent there may be some issues in going down beyond certain declination, but I don't think that should be a problem for
the South Pole is always at higher mass, even in the south, right? So if you're at 30 degrees south, it's always at one point in the south.
Right.
Yes.
And because of, especially for the cosmology drive, not only you want uniform coverage, uniform meaning at similar depth. And if you have a region with very bad air mass all the time, so for the theorists in the room, that means your observations are not quite as deep compared if you're observing overhead, because light has to go through much more atmosphere to get to you. So yeah, this sounds like good reasons to leave it out in favor of depth and uniformity. Yeah, that's a better answer. Any more questions? Well, I'm glad we worked that one out at least. This is what the current cadence is. So let me flick between the previous and the next. It doesn't change radically, which is fine. Also, there was in the mandate that the survey could change by no more than, I think, 10% compared to the original plan. So that they would meet all their requirements for a number of reasons. That's the space where they had to work in.
So there's a version 5 now? When did this come out?
Where were you last week? Teaching here? You have to be in Tucson. It's just come out. So I think now we're down to like 2 possible choices for the final cadence. Is the end of what people at Caltech call it the cadence wars of all science cases, you know, making a pitch for their own case and bad mouthing the other. But you can tell, for example, the first problem I personally would have seen here is what's this? Like the galactic plane doesn't work like that. You can't just say, oh, anything that is, I don't know, what is this, 10, 20 degrees off the plane is extragalactic and everything else is not. It's very inhomogeneous, right? So in a map like this, for example, you can consider extragalactic as part of the main survey, maybe all points that have a certain extinction less than, I don't know what they chose, 0.3 or whatever. But that's fine, that's more realistic to me. You can also see the galactic plane, especially, I think here's the region right of the galactic bulge. You have a high number of visits compared to what was before. And that's great, for example, for synergies with other instruments such as Roman, that will observe the galactic center at high cadence in the infrared. So that's going to be a gold mine. Yes.
Are the yellow points restricted to short intervals of time within the 10-year survey?
That's thanks for the question. We can mention that now. So these are called the deep drilling fields. So these are fields where the telescope will go back over and over again. So on a given night, it will not observe all the deep drilling fields, maybe 1, maybe 2, maybe some. Again, it's not super uniform as scheduling, But yeah, the idea is whenever is a night that the deep drilling field is observed, it's going to receive dozens of observations on each given night. Any more questions before we move on?
Yeah.
Yes.
What for?
For the deep drilling field?
What kind of science?
So at different times throughout the survey, the objective kind of shifts a little bit. At the very beginning, it will be important to have deep drilling fields to achieve the 10-year depth in just a few months, at least in some spots in the sky. So you can already do some of the science, or at least verify, can you do the science you promised? And not in theory, with the real data. Another reason is to study stellar variability, AGM variability, at a much higher cadence that is allowed by the main wide, fast, deep survey. So the variable sky for sure, and transients as well. The problem is that these are just 5 fields, I think. So it's about 50 square degrees. And no matter how deep you go, for example, F-bots, some special type of TDs, kilonovae, for the rarest transients, it's going to be really challenging to find them in deep drilling fields. But hey, if you do, exquisite data set.
How do they choose the deep drilling fields? Like, do they just was it random, or are they looking at specific objects or areas that they know are going to have something interesting? Or
yeah, may I ask, what would you do if you can take a moment, think about it? How would you pick them?
I don't know. I guess I'd figure out some sort of interesting object that we know is there and just.
Yes, so maybe a cluster, a globular cluster, or a galaxy cluster. Any other ideas?
Maybe somewhere another survey will look. So you get...
Okay, so for synergies?
I was also thinking where you have archival data very far back in time.
Exactly, so synergies in real time, but also synergy with respect to previous surveys. So some of this field will be like Cosmos, which is by far the best studied field so far. We have plenty of HST, GWST, radio survey, everything happening there. So you can do immediately excellent science, and you can just add to this wonderful legacy data set for humanity and all sorts of science cases. Any more questions?
So I get the pros of a non-uniform cadence are like you can adapt to weather and seeing and stuff. What are you losing by not having a super regular sampling in a survey like this?
May I ask actually your peers if anyone has any idea how to answer that? What do you lose by not having a very regular cadence?
If you have anything that's periodic, so kind of you need your cadence to be, good enough for sampling the periodicity, and then kind of you can't promise that.
Yeah. Agree? Just beware of aliasing if it's too regular. You may get some spikes in your periodogram that are artificial, that come from too regular. Sorry, but we're not going to risk that with Rubin. Any other ideas? What do we lose by not being regular? Well, for example, we may miss out on identifying, recognizing what we're looking for. We have maybe some sparse data points in different bands, and I look at it, I'm like, what's that? Is that transient? Sure, we can all agree about it. But is it a type 1a supernova? Is it a TDE? Is it an AGN? The fact that you have something more regular typically helps with the identification process. And also if you have a very advanced machine learning algorithm for classification, the fact that you have such sparse data set may not necessarily help in that sense. And also rates. So your inability of recognizing confidently what you're looking at will make it hard to establish rates in this unprecedented manner that we claim we're going to do. All right, so 30-second exposures or 2 times 15. Try to go beyond what Kishalay, I learned your name is not how I've always said it. We've been friends for what, 7 years? Yeah. Sorry. We're still friends. Kishalay. Go beyond what Kishalay said. Because, no offense, but it's not the whole story. Which one would you prefer and why? Discuss with your neighbors. 1 minute. Go.
Yeah.
I have not done it, but I think so. When Fed was giving her talk, I was sharing another session, so I didn't hear the difference. So this is I just took the slides. All right. Who would prefer, by raise of hand, if you have to make a choice, there is no right or wrong answer, okay? This has been a long debate, and there is not someone smarter or dumber in the decision. It's more like what your science drive is and a lot of other factors. But by raise of hand, who would go for individual 30-second exposures? 1, 2, ish. It's not an easy thing. I'm not expecting you to know. Gut feeling. 30 seconds. Okay, a few more. Who would go for 2 times 15? All right. Thank you. So Kishalay mentioned one of the reasons is to detect fast transients. 2 snaps. Maybe you see something evolving rapidly. Great, I agree with that. Tell me another reason why this could be a preferred option.
Rejecting glints from near Earth objects.
Rejecting Earth, or yes, so you further improve on solar system science versus rejection.
Like satellite jump.
Yes, and also not just asteroids, but everything that happens near our atmosphere. Good. Anything else?
If one frame is bad, you still get a frame from that.
Okay. Yeah, I don't think there was a plan to pick one, but rather stack them. But that actually is something that people could look into to get even deeper with maybe lucky imaging or other techniques that are based on picking the best.
Similar arguments like cosmic rays.
Okay, so rejecting the bad stuff. Who likes, yes.
I was just wondering, I mean, if it's very sensitive, then will you have sources like you'll get too many photons in one pixel?
Saturating sources. Rubin saturates at 17 magnitudes. That's the detection limit of a lot of telescopes. Okay, so if you do that, you really reduce the number of saturated sources. That's I think with the rapid variability, probably the main drivers to it.
Wait, sorry, you go 17th mag in 30 seconds?
Yes.
With saturation?
Yeah. It's something. So no, you're not going to study Vega with that.
Everything I need to know.
But that's okay. You can use a different telescope. Use ZTF, it's pretty good. So this has been, once again, a long iteration, a lot of pros and cons. The main problem of 2015 is you put those extra couple of seconds for the readout, 2-3 seconds. But I mean, it's like in life, you know, if you're addicted to a lolly that costs $1, you buy one per day, it adds up, especially if you're a PhD student. If you're an astronomer, it adds up to 6% of your survey time. It's a lot. So the very latest is that 1 times 30-second exposures will be employed and not the 2 times 15. So, sorry, man. I know you were a fan, but it's not going to happen. I'm happy because for extragalactic science, it allows you to have higher efficiency. So you can go deeper immediately. You don't need, basically, you can take more pointings, more images. That's it. Also, in U-band, so the bluest one, the decision was to further increase the exposure time to 38 seconds. That's to compensate for the fact that it's less sensitive, and even more that they made it even less sensitive. I'll show you in the next plot. The deep drilling field will use this ocean strategy. Very new wave, the way, yeah, that. They're still testing it. So on it, I don't have a lot to say. It's just a new survey that will have different constraints on how you dither, so move the telescope a little bit every time. And quite relevant for people who like multi-messenger astronomy, but also potentially hazardous asteroids, neutrinos. Now we have a target of opportunity program, and this will be a pretty big part of Wednesday's lecture. This is also how the throughput for filter has changed with time. So on the x-axis, a different version of the baseline, starting from, before 2015. You can see U-band has a huge drop. This is for a change in the technology that they agreed on, but that's the cost for all the other filters to go up. This is, again, the type of aluminization you do for the mirror. And the reason also why with time it keeps decreasing, they're making simulation more and more realistic, adding more downtime. What about the wide, fast, deep, the main LSST survey? Actually, something I had on the slide that I didn't mention out loud, I think is important, is that LSST was originally the name of the telescope, Large Synoptic Survey Telescope. When it called Rubin, they had to drop LSST, but for a lot of reasons, including money reason, like for funding and so on, they had to keep LSST. So they came up with what does LSST stand for now? The Legacy Survey of Space and Time. So it's fine to call it still LSST, just beware it's not the telescope, is the name of the survey. And LSST encompasses multiple surveys. The main one is called Wide Fast Deep. It covers, I think they keep the number it goes around is 18,000 square degrees. But if you add the additional areas that they talked about, it's more like 19.5, something like that, 1,000 square degrees. Another key point of the Cadence collaborative efforts, we'll call them worse. People actually, Rubin got so mad at me once because I said that, but because everyone has to be friends. But it's fine, whatever, like all this, just trying to balance everyone's needs is that for those who need high cadence, you don't really want to just make one snap of a field, move on and come back only 3-4 days after. Just not enough. So one solution they came up with is to divide the sky in stripes. And 1 year we'll do one stripe in declination at high cadence, and the rest at low cadence, and then swap. Here, actually, you can see a video. On the right side, you will see the cumulative number of visits. On the left side, you will see how it goes seasonally. I think this is integrated with like 1 month snaps. And it's actually the opposite. I apologize. Sorry. To the right is the seasonal, to the left is the cumulative. What you can appreciate here is that the stripes keep switching from 1 year to the next on the right-hand plot, but ultimately the coverage will be uniform. So people doing galaxies, large-scale structure and so on are happy in that they can do their science. So that's the plan. Although there are problems related to when the data are released, if it's uniform or not, so there are some complications to it. We already talked about a little bit of the deep drilling fields. So each deep drilling fields, or DDF, will have in total about 20,000 visits. Other spots of the sky, I think the average is 820, like the median, I think, is 820. Again, this number keeps floating as total visits per point in any band. Deep drilling field will be 20,000, and Cosmos will have twice that amount. Pretty good. How were they chosen? All the answers you gave are really good. And as you can tell, some of these fields are synergistic for other surveys and or legacy field, as they're called, because of the archival data. Any question before we dive a bit more into galactic plane and the mini surveys?
Can you explain what's currently the status with TOO and gravitational wave follow-ups?
Yes, will you be there on Wednesday?
Okay, okay.
Because if so, that's literally like 1/3 of the lecture will be, well, maybe not that much, but a very big chunk will be about that. Do you mind if I save it for it?
Sure, sure.
I can tell you, yes, it's going to happen. Yes, it has already happened. Things are looking pretty good.
Excellent. I'll wait till Wednesday.
Awesome. Thank you. So the galactic plane, like we discussed before, the original plan was not very light. It has some issues. So now what they recommend is adding some pointings. So you have better coverage of the Magellanic clouds as well. Often the science cases are kind of discussed together. In addition, what I found interesting is the definition of these pencil beams. These areas with higher number of visits, here you can see in yellow, that were deliberately put in random places. The reason is that you want to probe population trying to remove your biases, right? For example, you want to check microlensing. How do dark objects like black holes, for example, that cause microlensing distribute across the plane? Is there overdensities? Is it uniform? How does it work? If you want to study galactic structure, you need a more hybrid sort of approach. There's also the aspect of more static imaging type of analysis for star formation regions, clusters, so on, so forth. And you can tell how the microlensing detection capability changed from the very first proposal to now. It's by a factor, like 300%. So that's why we need this iterative process and input from the community.
So, sorry, the filling out the galactic plane will be done with a different telescope.
No, it will always be Rubin, just they changed the strategy such that there will be areas with a higher cadence, and for the other areas, it will be just fewer visits, unfortunately.
Okay, because it was the darkened region with the exposure time map that the first one was like. So that means there was very low visit frequency?
Correct.
Okay.
So that was the initial plan for Rubin, very low visits, very uniform. Here they made it not uniform, but with more visits. The reason is simply you have to work with a certain time budget. So what do you do with it? They decided we can't have that many visits as much as we like everywhere, but at least let's do it in some spots that we decide.
Right, this scale is very different, 0.8. It's just.
I know, I think this is like the additional visits that they've put in various areas. 8 visits doesn't sound like a lot, but it adds up when it comes to Rubin. If you imagine every time you double the exposure time or the number of epochs, you theoretically improve by 0.75 max. So it's not a negligible improvement.
Just when you say per visit, is that per filter? So it'd be like up to 8 visits in each filter?
I should double check Richard's paper, Richard Street's paper. Let me get back to you after I double check that.
This is over 10 years.
This is over 10 years, yes. Galactic plane aficionados had to, fight in a good way. And I keep using words that are a bit confrontative, just advocate for the science case strongly. The reason being, it's very hard to make everyone happy, but everyone's work contributed significantly to the final definition of the survey. That's the positive, real takeaway message. Any more questions? Okay, so what about mini surveys? So mini surveys are expected to take, I think, less than 1% of the survey time. So people were able to propose for mini survey up to now, at least for the first couple of years of operations. So the SCOC has selected a few and not all of them, but other mini surveys that were proposed will probably be carried out later during the duration of LSST. For example, the one about some star-forming regions. Let's quickly run through them. I see where are we doing with time? Yeah, doing pretty good. Okay, so the total area for the mini surveys will be around 7,500 square degrees. One is the North Ecliptic Spur. So the idea is to get up to 10 degree in declination. The main driver, as I mentioned before, get solar system object. You want to have an excellent census. And without that addition north, you would miss out on millions of objects. And this survey, by the way, is going to be in all the filters that are going to be there on the wheel more often. A little note, there are 6 filters, but the filter wheel has 5 spots. Sure. So they're going to swap out U and Y. Guess when U is not on the telescope?
When the moon is in like a fuller phase.
Correct. So it's not about what you're looking at, but depending on the lunation. When moon is bright, you will remove U band, you will put a near infrared instead that is way less affected by lunation.
What like lunation percent are they switching at? Or is there more time for Y or more time for U?
I think it's equal. Will be equally split. Yeah. The dusty plane, I don't know why it's interesting. They didn't call it the galactic plane survey, but the dusty plane survey. Well, unsurprisingly, it's going to be on the galactic plane. It's going to add observations over there. It's basically just complementing the wide fast deep. The idea is let's add as many observations as possible to get to 220. That's kind of a number they came up with that based on their metrics would allow people to do their science, minimizing impact on the other science cases. And then there will be the South Celestial Pole. Once again, here it's more like just give us some pointings to observe also another region of the sky that we can observe where there are objects of interest or supernova as well. So good for the dynamic sky, but I think more for studying more as a whole, all the celestial sphere in a more complete manner. Yes.
What's the difference between a visit and a pointing?
It kind of depends on context, I think.
Well, when it says 115 visits per pointing, what does that mean?
I think in this case, pointing means a certain array and deck pair. So for each point in the sky, it's not a very happy way of explaining it. Actually, thank you for letting me correct it. That's actually how it's on their survey strategy website. I just took the same verbiage, but I agree. Typically, you can say a pointing is when you move the telescope and you point somewhere. So there is a bit of confusion, but for each point in the SCP, you're gonna have, in this case, 115 visits. And not only there are mini surveys, but there are micro surveys, even smaller than that. But that's fine, you know. Like the smallest amount of time you can use to do your science, the more it's going to be appreciated, it's more likely it's going to be executed. That's kind of the rule of the thumb. And once again, this is a survey in favor of the study of asteroids, in particular, all those that are the closest to the sun. So this will be a twilight survey. At the moment, Rubin is not observing in twilight. That's something I learned only last week. Apparently, they don't have a safety device to cover LSST in case they don't get stuck and the sun rises. So that means the instrument can fry. It's like it's not okay. So what I learned is that until that's in place, they're going to interrupt operations 1.5 hours before sunrise. Why 1.5 hours? Any idea? I needed someone who does instrumentation for this.
I don't do instrumentation, but is that the length of time it would take to manually cover by humans?
Basically, to ask for help, let help come, like the technicians, and have them forcefully close the door, do something manually. Yes. So it's a very human, yeah, human
I was just
driven.
imagining a tarp, like, let's just say this giant
Anything.
Home Depot.
I was seeing all the staffers just literally going like flies on the mirror just to cover it. I mean, you don't want to waste LSST, right, over this. So anyway, there will be a lot of, I think, exciting discoveries thanks to this survey. Yeah.
How don't they have like a canvas sheet on like a?
It's not in place yet, but again, even in that, whatever they have, they need some safety time to just don't run into any risk. I think that's simply the rationale. And they estimated 1.5 hours is good. But for example, there was a binary black hole merger. We wanted to follow up with Rubin last week on the 27th of July, and we could not do that because it was too close to twilight. And that's when I learned that there is this limitation. Now, don't read this. This is on purpose to overwhelm you. This is to say, a lot of papers have been published for the optimization of the survey. So a lot of, in many cases, students like you or postdocs have put months of their time towards this effort. So first of all, personally, I'm very grateful for everyone's contribution. All these papers come only from the Transient and Variable Star Science collaboration, which is one of the, it's the second biggest collaboration, has 646 people at the moment, and I'm one of the 2 co-chairs. That's why a lot of what you're hearing is about the changing sky. quick note, I'm also chairing the users committee. So if you have any complaints you want to arrive to leadership, the Ruby users committee can help with that. You don't have to contact directly the director, we can advocate for you. Here is, yeah, just another example how for like type 1a supernova over time, thanks to all the feedback, you can improve detectability. Let me go a bit faster. And I've seen some of you already having a bit too much. So let's take a moment to just enjoy a couple of pictures because come on, astronomy is good for pictures. This is the community team. They have a community. Oh my God, I need a break. This is the commissioning team. Now, can you spot the person in charge of the commissioning that everything goes okay? Tell me stop. Keith was excited, but you know, a lot of weight on his shoulder. He was, yeah. Keith Beshel.
Zelko is also there.
No, Zeliko here is the director.
Yes.
Keith is in charge of commissioning. So Zeliko is probably going to be very mad at Keith. These things don't go well. Anyway, this is, I think the focus should really be on the faces of really people being in awe, seeing the first images ever being taken when they opened the shutter for the first time. And they're now carrying out a science validation survey. So this is going to be similar to the final LSST. It's going to be conducted from now to September. And it will also be relevant for the TO part, especially this bit. Photos. It exists, it's observed. This is all real. And this is what it looks like from inside. Probably many of you have already seen some publicly released images of Rubin. But seeing the telescope next to people, I think even the animation that Kishalay showed earlier doesn't quite render what a large piece of equipment we're dealing with. Galaxies, these are the first look images that have been released on June 23rd. Just, I don't know exactly how many images were used for this quad. This is not too far from what we expect from the 10-year survey though. And you can also browse that on Sky Viewer. So can pan, zoom, just look it up online. It's truly amazing. And the detail which these galaxies can be studied almost like space, as if they were observed from space almost, but you're doing it at scale from the ground. Something else that maybe not everyone knows, these images are subpar in quality. So the quality of these images is not good enough to make it to LSST. They said very openly, like, they look good. So, I mean, even us, we don't have quite, just looking at this image, we can't quite say, oh, obviously the PSF is 0.1 arcosecond less than, or more than expected. But just think of that. Quality will further improve from what you see here. More galaxies.
For these images, which filters were used for the RGB channel?
I'm not sure.
Okay. Because these are color images. I
Yeah.
assume some 3 filters were used for R, G, and B.
Yeah, I don't know which one they
Oh, sorry,
picked.
just to make sure. So usually when you construct a color image out of real CCD data, you have to, color images are composed of 3 components, the R component, which is red, green, and blue components. Usually you take some combination of filters and you assume those are close enough to R, G, and B, and you put them together, which is why from this image, it's not obvious to me, at least, that which of the 6 LSST filters were considered to be RGB in these cases.
I have the answer to that.
Oh.
So B is 0.3 times U and 1 times G. And then G is 1 times R. And then R is 0.05 times U and 0.95 times I.
Wow, okay. Thank you.
It's nice that they actually report so people can also maybe play around themselves. Thank you. The reason why I'm showing this one in particular, besides it looks pretty, look how good Rubin will be for low surface brightness studies. And be of galaxies, of maybe galaxies that are very low mass, that don't have a bulge, also for streams around the Milky Way, and in general, all the low surface brightness science is going to be revolutionary for that. But yeah, if you like the galactic plane, one of the challenges that I haven't heard said by well, someone said that you need very good photometry. Doing crowded field photometry is still extremely hard to do, even if you have like DOPHOT and some algorithm that can do that for you. This is technically a major challenge. In the last few minutes, ZTF work with alerts, meaning you have the, yes.
Sorry, before you move on from the images, last week, did you happen to hear for like on the actual camera, like what kinds of PSF widths they're getting with the adaptive optics on the site and everything?
Yes, so it's a bit of a moving target. So it's not like one fixed number. I say that now they're tapped into the minimum requirement, which is better than I think 0.9 and pushing down below 0.7. I think that's where we are at. I can, if you want, I can point you to the talk in which they talked about it. Getting better and better though. And there is the design goal, but also the minimum requirement. The two are not exactly the same, but they're getting there. So this is ZTF, it's not Rubin. You will have the new image, the old image, you do subtraction, a packet, which is basically a JSON file with information about when, where, and by how much a source has changed in sky will be delivered to you. How? Via brokers. So all these brokers are public services or platforms in some cases. Not all of them have the actual web platform, like Ample doesn't use it, for example, or Boom doesn't use it. But most of them do. This is going to be open to everyone in the world. No problem with data rights. For catalogs and pixel images, you need to have data rights, at least until the data releases. Ask me later if you, for any reason, are interested in knowing more and how to navigate the data right issue. And just going back one slide, ZTF on the median yield of alerts is 300,000 per night. They say Rubin will get up to 10 million. So we're going to be a few million per night. So again, pretty challenging. And the delivery time is expected to be less than a minute. The Rubin Science platform, probably you will use it this afternoon, is probably the best way of playing around with Rubin data. Now, data from the data preview 1 are up there, are uploaded. You don't have to download the data and then do the analysis on your laptop. You can do it directly on the platform. That's much more efficient on so many ways, on so many levels. So take the time to explore the various ways that are brought to you. And in the last 3 minutes, I would like to just give a quick, just for a moment, just take off my Rubin hat and put my University of North Carolina hat to say a few words about these instruments that is being built at University of North Carolina. The PI is Professor Nick Law, that you see here in the picture, with a bunch of the graduate students. John Carney, sitting here, is the one that will answer all your questions about Argus these days, since he's also part of the team. The idea is, how can we build instruments to do imaging of the whole sky at once? The whole sky, at least everything overhead. And then we'll see why it's relevant for Rubin. EveryScope was the first concept that was brought to light. The shape is quite interesting. It's like this dome with, you see, all the small telescope coming up in every direction. And then the idea is to create these very large images by co-adding frames that are placed next to each other. Now, how can you bring this concept to the extreme? The answer is Argus. It's going to be an orchestra of 900 telescopes. Think about it. It's 900. It's also with Kishalay mentioned in the talk, in the lecture, that multiple exposures can be convenient also to go deep. You can also find all the equations that tell you that multiplying the number of telescopes is convenient over having one very large mirror. It's way cheaper and you get arguably better results. So you're almost getting to Rubin size by employing an array of small telescopes. The resolution is not going to be as good as Rubin, obviously. It's 1.5 arcoseconds per pixel. It's pretty good. It's just less than a factor of 2 as worse as ZTF, which is pretty excellent. And something I'm quite excited about is how the team thought not just about the hardware, how to observe, but how to do the data processing. So there will be stacking of images every, I think, 15 minutes, 1 hour, every few days. And thanks to that, they will reach about 24th magnitude depth in 2 filters every 5 nights. One Rubin image, what, 24.5 Mach, getting close. But the best thing about Argus is the field of view, about 8,000 square degrees. And the way Nick, I think, likes to explain it is, if you lay down on the grass at night and you look up, that's pretty much 8,000 square degrees, what you can see with your eyes in that moment. And yeah, again, in this plot, maybe you can see how the power of this instrument is to unpack all the time scales, of course, at the cost of depth compared to Rubin. The reason why I'm presenting it to you today is how it can be complementary, a facility to Rubin in this area of big data for time domain astronomy. And thanks to the CMOS detector technology, the readout is milliseconds. It's millisecond, right? Way less than a second.
I don't know the exact number that's current. It's less than a second. We can do 1 second cadence and we can process everything and generate alerts at 1 second cadence, which we will do in bright time. And we'll do 1 minute and co-added in dark time.
Thank you. So that's also one more reason why it's complementary to Rubin for the brightest objects. So no saturation at 17 Mach here. No problem with that. So just to wrap up, in terms of, yes.
What 2 filters is it, and what is it expected to?
The filters are not officially set. Right now, it is probably going to be a G-band filter that's scripted slightly blue and the same R-band roughly that's in ZTF, but that number, or those numbers are subject to change, and if it affects your science, you should tell us, because we have not. The closest thing we'll have to Cadence Wars is Filter Wars. So if you want to throw fuel on one side of that fire, you should tell us, and soon.
How do the filters work? Like, how do you get full sky?
Yeah, so what it is, it's 900 telescopes in a trench coat. Each telescope is an 8-inch telescope that is from a company called Planewave that makes off-the-shelf telescopes. So the whole idea of Argus is gallons of the universe per minute per dollar. And what we do is we take 900 of these, we multiplex them on one mount. That way you have very few moving parts, because if you were to make a field of 1,000 telescopes, they would break all the time. You have horrible uptime. But the way the optical train works is you have the telescope, and then you have a focuser, and then you have an off-the-shelf astronomical camera that a wealthy amateur might buy. and the filters are going to be integrated into those cameras.
So it is still like you take one image in G and then one in R.
Yeah, so you're probably going to have stripes within the bowl Igor showed, where you're going to alternate G and R, and we may pepper in something like U and something like I. That's to be determined.
When does the LSST survey actually start? Like when will alerts start?
Thank you. That's actually a slide I should have put in. There were going to be major reviews in September, October for Rubin. I think now it's about mid-October. The LSST survey will likely start in November. Alerts may start to be issued as soon as September, however. It very dependent on how templates are generated for image subtraction. So probably will be very few, comparatively speaking, very few alerts to start with, and then we'll build up as time goes by. I'm just aware of the time. We don't want to go fast. So just conclude by saying, we're really going into a new era for optical astronomy, for all wavelengths. So let's be aware of that and how to make the most of all surveys that are coming online now. And I will leave you with an inspirational quote from Vera Rubin herself: "Don't shoot for the stars. We already know what's there. Shoot for the space in between, because that's where the real mystery lies." And that's all.
Any questions before we head out for lunch? One quick reminder, today's afternoon session will be about making real discoveries in LSST data. So please sign up on the Rubin Science platform if you have access, and please share access with your colleagues if anybody doesn't. Okay, any questions? Okay, good.
Well, thanks for the talk. I think I remember someone mentioning that there was it 8-hour embargo on the images?
80.
80.
80 hours
Is that
embargo.
still
So the alerts will be issued immediately, but catalog, especially the pixel data, will not be released before 80 hours from when the photons hit the camera.
So like the alert brokers that have like the little cutout stamps, will you not be able to get like the page for that and see the image? You just get the alert and dump it back in.
You mean the page, meaning having them displayed like I did? It's kind of, so some brokers actually have a service for visualization, but otherwise it's really a couple of lines of code. If you want to also do that on your end, you have both options.
Are the cutouts embargoed?
No, the cutouts are not embargoed, just the bigger images. And eventually there will be also a cutout service in case you want to see more context for what you're observing.
So just to clarify, as far as I understand, for DP1, which we'll be working with today afternoon, the cutouts haven't been released. So there are no alerts in DP1. It's just an SQL way of interacting with the data. But when the alert stream does start, you will get the cutouts that come for free with every transient. But for the time being, we're just dealing with sort of an SQL table where we can use some of that information to reconstruct the cutouts, which we will later on today. Okay. Thank you, Igor, again.